on this computer. All right. Okay. Before we start, just thank you for coming. We took time out of our busy finals week to be here, and so did you. So thank you. Thank you if you're tuning in. For this, we had a very similar plan to the last review session. So our plan is to go through all the midterm exercises one by one. Some of them are easier, some of them are harder. We'll give you some tips and tricks along the way, maybe different ways to think about them and solve them. Pretty much that's it. So we can jump right in, I think, right?
Yeah, I think so. I'll also say I will probably plan to stick around for a couple minutes afterwards if you have questions that don't get answered during this time or aren't related to the actual practice questions. So we'll have a little bit of time for that at the end too.
Okay. All right, so let's look at the first problem. It says, exercise 1, the relation R subset of C cross R between cities C and interstates R, and then describes the set, describes which cities are interstate, an interstate goes through. The relation S subset of T cross R describes which of the 4 states an interstate is in. The following tables describe R and S respectively. So the first question says, give R as defined in the table in set notation. So this one, if you see in an exam, probably easy points, right? It's not so hard. All that you need to do is look at this table and you can go row wise and see, okay, you can read this as St. Cloud is related to, and then you keep going column by column, I-94. And then you go down the row and you say St. Paul is related to, and you follow visually I-35 and I-94. So then all you do is you grab and you set R, you start your set, and then you write the tuples. Now, what's something you got to be mindful about in terms of order in here? Someone tell me? Yep. Exactly. Cities have to come first. Why do cities have to come first? Because it says R is a subset of C cross R. Now, I doubt that Sebastian would try to play a trick on you, but you can see that this table could very easily be transposed, right? And in that case, the answer wouldn't change, right? Even though the visual process might change, okay? So just keep that in mind when you're doing the test. Make sure that you pay attention to this because this defines the order of the tuples in the relation.
If for some reason the order of the tuples isn't given for you, then make sure that you are consistent with whatever order you choose.
Mm-hmm. That's right. Okay, so then we just proceed one by one. First row, we write St. Cloud, and then I-94. And then, well, don't close the set yet. And then we do comma, and now that one we do St. Paul. And excuse my handwriting as usual. I-35, and again, one nice trick I recommend for you is you can do it like this, kind of like when you're writing lists in Python or something. You don't want it to be just one long line. You can do it like this, where you can grab each row and you make a line for each row. That's if you want to stay organized. That's a nice way to make sure that you're not missing anything, and then you can check your work a little bit more easily.
Also, if you hit the edge of a sheet of paper or something like that, you can do the same sort of thing.
Now, the same with Minneapolis. Now, I'm going to abbreviate this. And this one is also I-35. And then Minneapolis, we have another one, which is I-94. And then just 2 more. We're going to have Rochester, I-90, and Duluth, I-30. Okay, so if you do it this way, row-wise, then it's much easier to check, I think, your work. So that's one. Do you guys want to do the other part, or should I?
You can take the rest of one, and I can do.
That's good. Okay, so this is a set notation. Again, you got to be careful that the tuple order is correct. You can read the tuple order from here. If this is not given, if you cannot determine the tuple order for the problem, you can assume, but you might want to make a little note. But again, I'm pretty sure that we're going to give you tuple orders. Okay, so I'm gonna need some room. Well, I might not need some actually. So yeah, part B says give S as defined in the table as a matrix. So for this one, we're gonna do just the matrix notation of relations. Again, this is pretty easy. And in fact, you already have it here, right? Now, again, if the table were transposed, it would be a little bit different. You would need to do a transpose, but essentially you just look at this and you say, well, there's nothing here, so I'm going to think of this as 0. Nothing here, so I'm going to think of this as 0. I'm going to think of this as 1. So just visually, you can already see the answer. You just replace the x's with 1s, and then the rest you fill it with 0. And that's it. Then, of course, you may want to move this here, and then you may want to like write it in brackets so that we know it's a matrix. And that's your answer. So rest assured, this is not so hard. If you see us in the test and it's as easy as this, then I think that's fair to say that's easy points, right?
The answer key specifies that you should reference in words which row is which and which column is which, because unlike the graph here, it doesn't actually have labels on it. So you can say the order of your rows and columns.
Yeah, you should. Are we requiring that in the rubric?
The rubric looks like it wants to require that, but it doesn't specifically say it, but it does make a note about it. So I think it's worth mentioning.
Yeah, in this one, we don't have a rubric in the answer key, so we can't necessarily tell you. Just, if you have some time, this will be a 2-hour exam. Likely you'll have more free time after the exam, then you have more time for each exercise.
We don't know exactly what the point breakdown Sebastian wants is, but the notes he makes on the rubric should give you a little bit of an idea of what things he's thinking about making points for, because those are the sorts of things that are on his mind as he's writing up answers. So he might tell us, take off half a point if they don't tell us which rows and columns are which, something along those lines. So the sort of thing to keep an eye out for.
Okay. So that's exercise 1. And now let's do exercise 2. So let me help you. Is there another eraser there?
Oh, I know.
We should bring one. We can
Bring one.
this faster. I don't see another one there.
Luckily, I don't have to drop tables for this one.
You can start your writing here. Erase. Here. Now let's start drawing the other parts. So, some pages.
All right. So for this problem, we are given a relation. We're asked about a couple of the properties that it may or may not have. So the first of these is our reflection. And so this is essentially a yes or no question, but you should probably add at least a little bit of justification. We don't need full proofs for this, because we're not giving you a property about the relation. We're just telling you what the pairs are. So you don't have to go through a proof, but some sort of justification for these. So can anyone answer with whether or not this one's reflexive? See some thumbs up. Yeah, so it is. And how do we know that?
1, 1, 2.
Yeah, exactly. So it has all 3 of those pairs that we need in order to be reflexive. So that's what we'll say. 1, 1, 2, 2, and 3, 3 are present. So just a brief little justification like that. That's all we want to a problem like this. All right. Second property, antisymmetric. Yes or no? What do we think? Hear lots of no's. All right. Why not?
Because there's 1, 2, and 2, 1 in there.
Yeah, so for this, if we're saying no, we want a counterexample, right? So some instance where the rule of anti-symmetry isn't followed. So in this case, 2, 1 and 2, 2, or sorry, and 1, 2 are present. But why is the pair 2, 1 and 1, 2 an example of not being anti-symmetric? Yeah?
2 doesn't equal 1.
Yeah, exactly. All right, and the third property we have that we're asked about is it transitive? What do we think? Yes, no? See some head shakes. Why not?
2 is 3, but not 1 to 3.
Yeah, exactly. So we've got 1, 2, and 2, 3, but not 1, 3. So justifications for these are pretty simple, but we want the combination of an answer and a simple reason why not, or why it is, in the case that it is. All right, then there is the, in my opinion at least, more complicated part of this question, because it uses at least in my experience, less common notation. It wants us to know what is r squared. Yeah.
You just take 1, 2, 3, and then just times it by itself.
Not quite. 1, 2, 3 is the set where our relation is on, is not our relation itself. And in this case, this is actually an instance of mathematicians having multiple different definitions for the same piece of notation. Usually when we have sets, something like this would mean r cross r, and it's looking for a Cartesian product. That's not what this is asking for. In this question, that's not what we're asking for. What is this question looking for? Ready? Yeah? Yeah, so it's looking for a composition in the same sense of a function composition, but we've sort of expanded that idea into relations. So we're looking for R circle R in sort of that function composition notation sense. Unlike with function composition, I'm not necessarily going to guarantee that a single input has a guaranteed single output. Right? So function, I put in x, I always get the same output every time. But here, I might put in x 3 times and get 3 different outputs. So I have to be careful about how I actually go about figuring out what all is in this composition. So when we're given the pairs like this, I like to think about it like I would a function. I just have to go through all of the possibilities instead of sort of just going one at a time. So I can think about having 1 as an input, and then 1 could be an output, and I feed that 1 back in again. I get out potentially another 1 as an output. But I could get a 2 as an output from either of those instances of feeding in 1 as an input. Right? So I have to take that into account. Right? So I could get 1, 1 by getting 1 as an output and then getting 1 as an output again. I can also get 1, 2 by getting 1 as the first output and then 2 as the second output. But if I get 2 as my first output, now I've got more options when I put 1 in. Right? Now I can get 1, then it outputs a 2. I put that 2 back in and I can get a 1, but I've already got that option. I can get a 2, I've already got that option. I can get a 3, that's a new one. We can continue this process, putting 2s as inputs and putting 3s as inputs. What we end up getting is all of the possible pairings of 1s, 2s, and 3s. And so a rule of thumb that I think is sort of helpful for this is that we can write down a rule for this in terms of something that looks very similar to the rule of what it means to be transitive, which is that if I'm comparing R and R squared, and I have an element A that relates to B in R, an element B that relates to C in R, then that tells me that A in R squared relates to C. So if you don't like thinking about these as functions, you can sort of think about this in a more relation-centric sense, in a rule that looks very similar to what we get for a transitive property. But we've got this R squared here, not mandating it's in our set R. It's telling us that if we look at R squared, we'll have that element. All right, any other questions about this problem? Before I hand it back over to someone else? Yes.
So what makes R squared different than the transitive closure R?
So in this case, this is in fact an equivalence relation, and it would be the transitive closure of R in this case. What makes that happen is the presence of these reflexive pairs in our original relation. You don't have some quantity of those or a sufficient number of other elements, then this is not necessarily going to have necessarily even all of the things that are in here, or the transitive property in and of itself. Yes.
Is there a specific order we need for R2?
Oh, so R2 is going to have no order sort of within the set, but the pairs need to have an order that sort of comes from this rule. So if you want to think about it in terms of inputs and outputs, your first input is the first option. You sort of don't write down that second input, and your second output is the second option. If you want to think about it in this way, then A and C have to match up in the right places. Yes.
For AB and BC implies AC. Do the AB and C have to be B?
No, you could have, like we had here with 1 R1 and 1 R1, which told us that 1 R squared. The only thing that has to happen is that the B's have to match up. That's why they're the same variable.
Yeah, and so if you had like 2, 1, 1, 2, then you can have 2, 2.
Yes. So on and so forth. Make sure I'm out of the way of this for a second. Anything else? All right.
Well, you can, if she's asking whether we want you guys to list out the whole relation or just the missing ones. You can compactly say R union the missing ones.
Yeah.
So we don't need you to write it all out. We're just doing it for illustrative purposes.
Yeah.
But you can very easily just do R union, whatever, because it's
Although,
set notation.
make note that R squared is not necessarily going to contain everything in R. That's once again, these reflexive pairs are making it such that everything that is in R has to be in R squared. But you could easily get a set where if you take R squared, you don't get everything that was in R. You can do it by removing some of the reflexive pairs from here. I did that the other day when I was messing around with this. And you can get an R squared that's not transitive and that doesn't include everything from R by just taking out a couple of pairs. So just be careful. You're not always going to be able to use that R union, although I suppose you could do R minus union, but then it starts to get a little trickier.
For when you're finding a closure, you can do that though. If you're just unioning things, you don't have to write out the whole thing. You can use R union, whatever you're missing in that context.
Yes, a closure will always have R in it, but R squared might not.
Yeah.
Another question?
Yes.
Actually, I think that's a good point. Actually, an interesting concept is that if compositions of R are always a subset of R, I think that means it's transitive. Something like that.
Something
It's
like
an
that.
identity in the book, if you're
Yeah.
interested.
That,
It's a
yeah,
theorem.
that makes sense.
Yeah, if and only if. So
Question?
Yeah, it's just asking to reiterate why is it different from transitivity?
Ah,
Like an example of that.
yeah, so transitivity would be a property that R itself is going to have. R squared is a new relation. So that was sort of a high level sense. That's the difference. Here, this rule looks a lot like transitivity because it actually is very similar to the idea of transitivity. We're just using it to create relationships in a new relation as opposed to mandating relationships in a given relation. If you want an example where R squared isn't transitive, we can probably do something sort of simple. Let me see. I don't want to take up a crazy amount of time on this. But let's say we had something like 1, 2, 2, 2, 2, 1. And 1, 3, maybe. I think this should give us something that doesn't behave as nicely as this one did. So let's call this S instead. And then S squared. This is just off the top of my head, but I hope it works out. We've got 1, 1 in here. We still have 1, 2. We would still have 2, 1. We would have 2, 3. We would not have 1, 3, 1. So yeah, so we would still have, so this would now not be transitive because I have 1, 2, and 2, 3, but I don't have 1, 3. And it's also an example where this is not a superset of this one because it's missing 1, 3. So it doesn't take all that many pairs to sort of blow away the idea that all of them are going to behave as nicely as this one does. Does that answer the question?
One last question is, would it be transitive if we were doing some matrices?
You could write them up as matrices, but that wouldn't actually change anything about the end results of the relations. So S squared is going to have the same properties regardless of how you represent it. So hand over here as well.
Should 2, 2 also be this? This 2 goes to 2.
Yes, good point.
Oh, sorry.
Anything else?
One thing, guys, is if you have some time and you want to like quadruple check your work, then if you know how to calculate square relations, the composition of relations using matrices, matrix multiplication, you can do that too if you have time.
Matrix multiplication can be a pain, so I'd save that for only if you have time.
Yeah. If you're done and you're like super worried and you want to do every method to check everything, you can do that. Although this is kind of, they're binary matrices, it's not so bad.
It's not the worst, but it's still not fun.
Fun. I don't know.
Danny, one last question. Why is 1, 3 not an S2?
Because there's no way to get 1, 3 as a composition of these rules or through sort of our function idea. If it were the case to get 1, 3, I'd have to put 1 as an input and get 3 as my second output. So if I put 1 as an input, the only thing I can get out is a 2. And if I put 2 back in, I can't get a 3 out, right? I could get a 2 out, or I could get a 1 out, 1, 1, and 1, 2, but I can't get a 3 from that second output. I suppose I could get 1 and then 3, but then I can't even put the 3 back in, right? So I can't get 3 as that second output. And so I can't have 1, 3 in S squared. Does that answer? Cool. Yes. So this one. So I can't write it with just a union. Although I suppose I could do S minus 1, 3.
Yeah.
And then union, what would I need?
Whatever.
2, 3. So I could get rid of the 1, 3 that's missing and then add in the 2, 3 that's addition. But I couldn't just use a union.
Right. Because if you were doing union, then this would be in the union and you don't want that.
Yeah.
Right.
So I don't want the 1, 3. So I can switch the ordering of these. as long as my grouping is good, right? I don't want to try to get rid of 1, 3 from this. I want to get rid of the 1, 3 from this. But yeah, we just want to make sure that the 1, 3 sort of gets out of our final set. So I suppose you'd have less writing like this. You just have to think about both getting rid of things and adding things in, as opposed to just looking at what the elements are. So, yeah. Yes. Anything else before we move on to the next problem? Anything else happen on the Zoom? All right, cool. Oh, that's good.
So almost to join those with that. It's tiny bit faster. How do I get to the next page on this? You just see bit. Very good.
Is that right? I don't think that's that right.
Yeah, that one gets tricky.
I'm guessing. Oh, I think okay. Let's go on that. And then you can talk about those while I draw next one. Oh, I should.
You should. All right, so I'm going to start talking about the problem at least. This one says, consider the following graphs: G on the left, H in the middle, and then we'll have F on the right. So this is just your typical isomorphism question. There's definitely going to be questions about isomorphisms in the book and the exam. So this is something that you really got to practice. The good news is that these are not so bad, especially this one. This one's pretty systematic. It's just a matter of knowing how to do it efficiently. So we know that isomorphisms are mappings that are bijections, meaning what? It's a mapping from vertices to vertices. And if it's a bijection, what does it tell us about the input set and the output set?
Sorry, on the middle graph from B5 to B1, I don't, or to U1, I don't think there's a.
Yeah, there's not an H from this guy there.
Good catch.
Yeah, that would have definitely been to me.
Yeah.
So what can we say? Yeah.
Every input goes to the, like every output is hit, also every input goes to one thing.
Yeah, that they're injective. It's injective and surjective. And in practical terms, if it's a function from vertex to vertex, that tells us that the number of vertices in the isomorphism must be preserved.
That's
From
a
the input
property
output.
of bijections in general.
Yes.
If you have a bijection between two sets, the sets have the same cardinality.
Yes.
And interestingly, that actually works for infinite sets as well.
Yeah.
But that's not really helpful for
Yeah. Unless we give you an infinite graph in the test.
I don't think that would be hard to draw. So
Yeah. Okay. So we know that they need to have the same number of vertices. So this is one of the invariances that you should check first, because you can rule things out. It's necessary that the number of vertices is preserved, and thus that both graphs have the same number of vertices. So I'm going to write this down here, that we should check the number of vertices. That's probably the first thing you should do, because it's super simple. So how many vertices do we have here? 1, 2, 3, 4, 6. 4, 5, 6. I can't count. 1, 2, 3, 4, 5, 6. Okay, so that doesn't help us in this case, and it's the final. We wouldn't expect it to be so easy, right? But it's something that you should know and you should check, because I don't know, maybe there's an easy one and you don't waste it all the time. Another thing that must be preserved is the number of edges, because isomorphisms on graphs specifically maintain the adjacency structure. So the neighboring structure must be maintained on each vertex once it's mapped. And we've talked about this in lecture, we talked about this in discussion, it's in the book if you want to review it. But that tells us that the number of edges must also be the same. It's just another invariant. Okay, so are the number of edges the same? We have 1, 2, 3, 4, 5, 6, 7. And here we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. So we have the same number of edges. So sadly, in this instance, it doesn't help us. What's another invariance that I should always check? Because these are super quick, right? You just count twice. Degrees, yeah, okay, well, yeah, degrees. So the nice thing about degrees is that you should actually do it because it helps you map, helps you find the isomorphism too. And I'll show you why that is. So
I recommend actually starting by pairing up the degrees once you've checked that it's actually possible for there to be an isomorphism, because the degrees will really help you narrow down some of your choices and make the whole process a lot easier.
exactly. So let's see what that looks like. I'm gonna go and on top of each node, I'm gonna write its degree, and then I'm gonna write them as a list down here. So this is degree 1 because it only has one edge adjacent to its neighbors. This one is degree 4. This is a really popular guy. This one has degree 2. This one has degree 3. This one has degree 2, and this one has degree 2. So I'm going to write the list, and the list was 1, 4, 2, 3, 2, 2. Okay, so this is this list. And if it's possible that these guys are isomorphic, then we would expect when I write down the degrees of these vertices in a list that it'll be a permutation of this. Now the order will not necessarily be the same. That will be too easy actually, especially if you go like by sub-index like I just did, then there will be no problem to solve. So that's what I'm going to do here. So I'm going to start with B1. This is clearly degree 2. B2 is clearly degree 2. I don't know what that is. Oh, 6. Okay. I say that. This is degree 1. This is degree 4. This is degree 2, and this is degree 3. Okay. So now I write the list: 2, 1, 4, 2. Oh, wait, what?
If you wanted to do the same order, you skip that.
Oh, yeah. 2, 2, 1, 4, 2, 3. Okay, so are these lists permutations of one another? Yes, because we have 1, 4, we have 1, 1, and we have 3 2s on both lists.
And we have 1, 3.
And 1, 3, yes. So now writing the degrees is so easy because in the instances in which you have vertices that have solitary degrees, if they're isomorphic, then if you have one single vertex that has degree 1 here, then you would expect one single vertex that has degree 1 here. And that allows you to relate them because there's no other option. If I map this guy to any vertex here, it needs to be mapped to something that has degree 1. And there's only one option. So what does that tell us in terms of isomorphisms? It tells us that if you have an isomorphism F, that B1 must be mapped to B3. Probably should call them U's.
I think it does call them U's.
Which one's B, which one's U? Okay, these should be U's, so I'm gonna write them as U's, okay? Just to not make it confusing.
And then here, and I'll make these W's.
Okay. Okay, so that's 1, and we can do this for all of these guys that have degree well, that there's only one vertex that has that degree in both. So we did it with the 1. Now we can do it with the 4. There's only one guy in each of these that has degree 4. So in this guy, it's B2. So I'm just going to make a table instead of writing the F notation, just because it's a little bit easier, right? So I'm going to say X, and here I'm going to do F of X. Hope this is legible-ish. And this is going to be B2, and B2 is going to get mapped to U4. Then I'm going to keep going, and I'm probably going to need to extend my table here. Sorry, a little bit messy. And now I'm going to look, okay, what is the other one that has one only kind of a unique degree here? Well, this one's the only degree 3 vertex. So I'm going to say B4 is going to be which guy? is going to be B6, U6. Okay, so we're halfway done and we didn't really even do any thinking. We just did matchy here. Now we do need to think just a tiny bit more, but we can already use some of the adjacency structure that we discovered here in order to figure this out. For example, B5, well, which one would be a good one to start here? B2 and B4, okay, B3, B3 is an easy one to start with, right? Because we see here that B3 is joined to things that we've already know what they are, what they correspond to. We see that B3 is exactly connected to B4 and B2. So we would expect the vertex that B3 gets mapped to, if this adjacency structure is maintained, to be joined with specifically U4 and U6. So all we need to do is look in this graph and find a vertex that is joined only to U4 and U6, and that would be,
And also that has degree 2,
yes,
but it just so happens that everything that's left has degree 2, so that doesn't help.
it is joined only to those two things. So that also kind of implies it. So there's many ways for you to kind of arrive at what you need to find. There's many ways of solving this. There's many ways to think about it. You can think about it like in terms of ruling out degrees, in terms of looking at adjacency. There's many ways to proceed. So don't feel like you need to do it in the way that we do it. Find the way that works best for you and that it's kind of proven and sensible to work with. But this way is pretty systematic also. So it's replicable in many different graphs. So, okay, so we want one that gets mapped to U4 and U6. So this is U6 and this is U4. So which one is mapped to both of them? It is this guy, U1. So then we say that B3 gets mapped to U1. Okay, so now we need, we have these two guys. These two guys are mapped to each other, and each of them is mapped to something we know, right? Because on this side, we already know all of these guys. So now it's just a matter of saying, okay, B6 is mapped to B2. So now we just look on this side at the two that we have left, and we see which one is connected only to B2. So which one here is connected only to the B2 equivalent? The B2 equivalent is U4. So we look here, and this is U4. So which one is connected only to this one that we haven't seen yet? It will be U5. So U5 and B6. And then we have just one left, and that would be B5. And the one that we haven't done here is 3, 4, 6, 1. So it will be U2.
Double check that last pair follows all the rules still, because it could be that the last one you get to is the one that doesn't work out for the isomorphism. So check that the rules still hold on that one.
Yes, and another thing that you should check in your isomorphism is that, like one of the folks here said, that everything gets mapped to, and everything maps to one thing in terms of injectivity and surjectivity. So we need all of these sub-indices to be different. If we need them to cover all of the sub-indices here. Every one of these guys needs to be present here exactly once. Every one of these guys needs to be present in the other column exactly once. So you need to make sure that's a good way to check, because otherwise you made a mistake. Okay, so now let's move on to the next part, which says.
One quick note, there's lots of different ways for you to actually write the isomorphism. You could do a table like this. You could just write the pairs as a set. You could actually make the set up the notation for a function and write the output of the function for each of those pairs. It also sort of boils down to making known what all the pairs are. You just have to be clear about having that, essentially having the list of pairings that the isomorphism makes between vertices and conveying that information somehow. So tables, the actual set, the function, any of those would work just fine.
I did the table only because I didn't want to write F parentheses a gazillion times, but there's many representations. Okay, so now let's look at part B. Part B says our H middle, and F right isomorphic. If so, give the isomorphism. So what do I need to do? I'm going to just go through my rules. It was number of vertices, number of edges, listing the degrees. Okay, so in terms of number of vertices, do we have the same amount?
Oh, and thank you.
Oh, yeah.
Yeah, could you also look out for like cycles, varying length?
Yeah, you could also look for cycles, and in
Yeah.
fact, we're gonna do that. Later.
So there's lots of more specific sorts of structures that are preserved by isomorphisms. You can get very specific, as we'll see with problem 8. That you can get really specific about what sorts of things are preserved. It just so happens that here, all you need to think about is degrees and edges, and you can do all the isomorphisms. So we don't have to get any more complicated than that. So we won't, because it's easy this way and easy to follow.
Exactly. So again, what about the number of vertices? Okay, we have 1, 2, 3, 4, 5, 6. Same number of vertices as this one, which had the same number of vertices as that one, right? Okay, so let's check the number of edges. 1, 2, 3, 4, 5, 6, 7. 7 edges. Again, in this case, it doesn't help. Okay, well, now let's list out the degrees like we did over there. We're going to start with W1. We're going to go in sub-index order. So W1 has degree 3, and W2 has degree 3, and W3 has degree 1, and W4 has degree 2, and W5 has degree 2, and W6 has degree 3. Curious. Here we have a 4, but here we do not have a 4.
Something else you could do, you could stop when you hit the second 3, because our other one didn't have a second 3. So you can do what computer scientists would call short circuit and stop when you know the answer, and you don't have to go any further than that. However, it can be nice to actually list out the whole thing in case you made a little error and stopped early. And it really doesn't take long to list out 6 numbers as opposed to 3.
That's right. Yeah, so actually there's many little steps in this test where you can use a little bit of foresight or a heuristic or some insight in order to do a short circuit and stop your search early. We'll probably mention at least one more.
There's another one. There's some in problem 8, I believe.
Yeah.
And there might be a couple others that we can point out, some sort of little tricks that you can sort of use as little time saves. If you can spot sort of how we came up with them and how you might see similar things in the final.
Yeah, luckily in this exam you'll have 2 hours. So you'll have a little bit more time. You don't have to super optimize for all the tips and tricks, but just something to keep in mind, especially if you're doing your first draft of a problem and you plan on going back to it. Okay, so we know that these 2 are not isomorphic now. And then part C says, use your answers in A and B to state whether G, left, and F, right, are isomorphic. And I mean, we probably all already read the answer key by now. So we know that the answer is no, they're not isomorphic. They cannot be isomorphic because isomorphism is an equivalence relation, meaning that if F is isomorphic to G and G is isomorphic to, if G is isomorphic to H and H is isomorphic to F, then if it's an equivalence relation, then it's transitive, just like the equality sign, just like the modulo equivalent congruence signs, just like all those things that we've already studied as examples of equivalence relations, then we would expect transitivity. So because it's not an equivalence, because these 2 are not isomorphic, then that guy and this guy cannot be.
So I will note there's other ways you can come to the conclusion that they aren't isomorphic. You could compare these degrees to those degrees, but that's not the kind of justification this problem asks for.
Yeah.
It wants you to use only the ideas that come up in the first 2 parts, which involves making an argument based around the fact that isomorphism is an equivalence, or really you only need the transitive part of it. And you can make your whole argument. So you could get the correct no answer, but we also want the justification to be in reference to the properties that isomorphism has, not just in reference to the degrees of G and F, for example.
And that's pretty much it for this problem. If there's no more questions, we're gonna switch to the other one. Yep.
Wrong way of denoting the matrices.
what would be a wrong way of denoting the mappings?
Maybe if you only gave 5 pairs when you need 6, that would be even if the 5 you listed were right, that wouldn't be an isomorphism because you'd need to map every vertex. So like, as long as you can convey to us which pairs of vertices are paired together, that should be sufficient for your isomorphism. I'll also throw this out there in I think in all of my discussion sections, I wrote up some slightly more mathematical definitions of a couple of the important things isomorphisms preserve. Would anyone like to see that, or are we happy just talking about the ideas that they preserve? I think that might help. I could put it on the Canvas page too, but I can also write it up pretty quick right now if you'd like. Okay, cool. So I'll set that up real quick. I just need a couple of pieces of notation established. So let's say I've got 2 graphs, G, which has vertices and edges, and H, which also has vertices and edges. And I want to have an isomorphism between them. I've done a lot of math, so we use a lot of Greek letters for isomorphism. So I'm going to call it phi, which goes from the edges of G to the edges of H. So phi is going to preserve, we talked about degrees. It's going to preserve the degrees of every single vertex. So in addition to having, which is sort of how we did a lot of that pairing. So if I've got a function deg that gives the degree of a vertex, and I have some vertex v1 that I put into it, whatever phi maps v1 to has to have that same degree. So it has to be the case that if I take the degree of whatever the image of v1 is, it has to have the same degree. So we can sort of formalize how we're talking about matching degrees. We can also start to formalize the idea of preserving edges and preserving relationships, or the neighbor relationship specifically. So if I've got an edge from...
Oh, there's a question over there.
Yeah.
Yeah, I'll have stars tomorrow. I think, unless I have a last minute cancellation announcement, I should have. There's I have like one thing that might become a conflict, but I doubt it.
If we have an edge that goes from a vertex v1 to a vertex v2, and that's in my set of edges, then it has to be the case that once I map both of these vertices, there has to be an edge between them as well. So the edge that exists from phi of v1 to phi of v2 has to be in H's set of edges. So these are the 2, in my opinion, most important properties that are preserved by isomorphism for this exam, partially because you can answer everything about problem 3 only knowing about these 2 properties. So essentially that gives you, just these 2 properties gives you at least 1 full question's worth of points. And you can also do most, if not all, of problem 8 as well with just these 2 pieces of information. Especially if you take note of the hints that problem 8 has. So I really think these are sort of the 2, if you don't remember anything else about isomorphism properties, make note of these 2. Yes.
So what does need to post on Canvas?
Yeah, I can put a little write-up on the Canvas page that includes these properties.
And yes, one last fun fact, some of you might take upper level math courses. Some of you might take modern algebra. This is what we would call either an equivariance or an invariance of a group action. So maybe you'll see something along those lines.
You may also see other sorts of isomorphisms. Isomorphism is not a term that just applies to graphs. We talk about isomorphisms amongst pretty much any kind of object in mathematics. And isomorphisms will always have properties that look like this that we call preservations. They will have, depending on what you have an isomorphism between, you'll have lots of different things that are preserved. But these are the sorts of things that you can use to test whether or not something is an isomorphism. So if you get something like that on this exam, if it says check whether or not this function between these 2 sets of vertices is an isomorphism, then these are the 2 properties that I would immediately go to check.
Yeah, if you want to take modern algebra for your upper division math course, I recommend it. It's a really fun class. it's more in light of this, like, there's not so much computation. Yeah, some people do like this stuff. It's very cool. Modern algebra, I'm a big proponent of.
I also endorse algebra
Yeah.
classes. I
Uh-huh.
love abstract algebra stuff. It's really a lot of fun. I think there's a whole lot of stuff to play with. So I will second that opinion.
Modern algebra is like you see the matrix, you see like the commonalities between all these different structures in math and computer science, and you study them at a level above, so you can like prove things about all of them at once. And then you can go one level deeper into category theory. I'm not there yet.
Any other questions about the graph isomorphisms we got slightly distracted from? All right, cool. I'll start writing up the next problem then. All right, aha, tree. Yeah, I know, right? Nobody does that group stuff.
What about exercise 4?
Did I skip a question? Oh, yes, you're right. I did skip a question. Thank you for pointing that out. I'll just go back and, yeah, Seal can do the trees. All right. My bad. Sorry. All right, so we've got a relation R on the sets A, B, C, D, E, given by R has 4 elements. We've got A, B, B, A, C, D, and D, C. And so we want to give a couple of different things about this. So the first thing it asks us for is the reflexive closure, which I'm going to abbreviate RC. So the reflexive closure of R. How would I figure that out? What do I need to make this reflexive? Yeah?
Like AA, BB, CC, DD, E.
Yeah, exactly. So we could use sort of the trick that Mario talked about earlier. I can say my closure is going to have everything that R has, because that does work every time with closures. And then we can union on exactly what was just mentioned, all of the reflexive pairs from these elements. And it just so happens that none of them are in there. So I have to go with all of them. I have to have AA and BB, etc. with CC, PD, and EE. So I can also list out all the elements, but we can shorthand by starting with what's in R. Yes. So the order of pairs doesn't matter. The order within the pairs still matters. Yes. So all of these relations are all sets. So since sets ignore order and multiplicity, all of our relations are going to ignore order and multiplicity as well. Is that a hand over there? Just stretching. Cool. All right. So we now want some other closures. I'm going to change the order of the question slightly because I think that the symmetric closure should be the next question and not the transitive closure. Yes.
Like if say like BB or like one of them was in R already,
Yeah.
done then R's.
Yeah. So if it was already in R, then it would be included from here, and I wouldn't have to list it here. Although if you did list it there, that wouldn't hurt anything. Does that answer your question?
So the R or takes.
Yeah, so the union takes care of that because whether it's in R or it's here, it ends up in RC. Yes.
Why do we still need to include?
Because E is in this set. And reflexive says anything that's in this set has to be related to itself. And so I need to have EE there because it's in this set, even though it doesn't appear in any of these pairs. Anything else? All right, cool. So symmetric closure, which is part C, not part B, but I'll get back to part B in a minute. How would I go about forming the symmetric closure? Yeah. Yeah, so it's just R, which is a nice, easy answer, right? Because I can take sort of at our sort of intellectual level, I can take all of these and flip it, right? Our intuition with symmetry says I can just swap the order of everything. And all of these, I can swap the order and I'm still in my relation. So I don't have to add anything in. And yes. Yeah, great question. So at least in my mind, it has to do with a little bit of distinction about what these properties are actually telling us we have to do. Reflexivity says for every single element of this set, I have to have a pair that relates that element to itself. Right. So our sort of mathematical definition says that if this set is A in general, that if I have any element A in A, so for all of those, then it has to be the case that A is related to A, or that AA is in R. Right? It mandates those elements all exist. That's what reflexivity means. However, symmetry sort of has a different style of mandate. It says that if I have a pair A and B from my set A, then only in the case that I have a relationship already do I need to have a different kind of relationship. So it only mandates pairs existing if there's already a pair that has certain properties. So if AB is in my relation, then I have to have that BA shows up in my relation.
You may be wondering why the distinction? Like, why is it that reflexivity works in this way, where it looks at elements of the set that the relation is operating on, whereas transitivity and symmetry don't? And the simple answer is because some old guy said so when he wrote the definition. Because it's useful.
The more complicated answer is because it makes it behave the way that we want equivalence to behave.
Yeah, it's true.
So if I think about the idea of equivalence on like the real numbers or the integers, the way that we've been doing in mathematics for many years now, you would want 10 to be equal to 10, right? And so if I want to, the idea behind equivalence relations is sort of replicating that idea of equality in a more general sense. And so if I want to sort of replicate equality on A, B, C, D, E, then I want E to be equal to E, right? In the same way that I want 10 to be equal to 10. So that's sort of a more complicated answer as to why reflexivity works the way it does there. But yeah, so I see these, I like to talk about these as sort of slightly different for alls, because this one mandates that certain pairs exist, whereas this one mandates that this property gets held. I saw hands as a question.
Can you go over what a closure is, just generally?
Yeah. So in a general sense, I like to think about closures as just supersets. So any closure of R is just any relation that includes everything that R does. And it should be a relation on the same set, but you could theoretically have something that's a superset that doesn't actually happen on the same set there. It's wild, or at least it could look like a superset. But it should be a relation on the same set. So I could have a relation on A, B, C, D, E, F that might look like it includes everything that R does, but technically has different elements because the elements are coming from a different set. So be slightly careful with that. But in general, I just think of closures as supersets.
Yeah, and to be specific, it is the smallest superset of R that has the relation that we want, the property that we want. So if we want the reflexive closure, then you think, okay, what is the smallest in the set of all supersets? What is the smallest superset in terms of cardinality that has that property? And that is why when you actually solve the problems, you think, what am I missing? and you think, what am I missing? And you add what you're missing to meet the property and nothing else. If you add something else, then you don't have the closure. You have a superset that may meet the property, but you don't have the smallest superset that meets the property.
The word the textbook uses, I believe, is minimal. We use that a lot in mathematics to mean the smallest such thing, with like the minimal superset would be the closure.
I personally actually really strongly dislike the explanation that the book gives on that.
I
read
really
it in
strongly
class.
dislike almost every discrete math textbook I've ever
Yeah.
encountered. So I don't think any of them do it well, but that's besides the point.
In
This
my-
one does some things okay.
In my sections, I read it out loud for comedic effect. So if you're not in my sections, you should go to the book and read it out loud to see how obtuse and complicated it is. Because it is really just the minimal, thank you, the minimal superset that meets the desired property of the relation, the minimal superset of the relation. That meets the desired.
So if you didn't put any properties, then R would always be its own closure. A reflexive closure has to be a closure that is also reflexive. So the smallest superset that is reflexive. All right, did any other questions come up in the chat? All right, cool. Great questions so far. All right, so moving on to part B, because I skipped it, because I like this order better. The transitive closure. I guess I'll note for the people who aren't in my sections, I picked this order because reflexive, symmetric, transitive is sort of the order in which these properties are easy to prove, in the sense that reflexive is always going to be your easiest to prove, then symmetric, and then transitive. And in addition to that, knowing that something is transitive is infrequently going to help you prove it's symmetric. But much more frequently, knowing it's symmetric can help you prove it's transitive. So I like to think about these properties in this specific order, because doing them in this order can actually make the harder ones easier for some equivalence relations. Whereas doing it in a different order can't really make the harder ones easier.
And also, if you know that you're gonna get asked whether something's an equivalence relation or not, you go by fail first, right? Like you
Yeah.
go by easiest, such that if reflexivity is easiest to check, and if you check it and it's not reflexive, then not an equivalent relation.
Versus if it is transitive, you've done all the work to show it's transitive, only to find out it wasn't reflexive. The easy one to check.
Yeah, that's another example of like ordering your computation such that you can short circuit and stop early.
And it turns out if transitive is the problem it doesn't have, or is the property it doesn't have, then you've done easier work to figure out that it didn't happen, versus if reflexivity is what it doesn't have, then doing transitive first would mean you've done the harder work. So it's sort of a nice default that sort of makes your workload the lowest overall, even if sometimes you might encounter something that does a little more work than you. All right.
Such thing as free lunch.
Yes, exactly. So the transitive closure, what would our transitive closure look like for this? Like the rest of them, we're going to have R, and maybe we add something on. What do we have to add in?
Over there.
And yes, all of them? Yeah. So we have to have AA, BB, CC, and DD, but not EE. Why don't we have EE? Yes.
Cause it's not like in R.
Yeah, so E doesn't come up in R, but that doesn't necessarily mean that, well, I suppose if E is never in R, that doesn't necessarily mean that E is not going to be here, but E could show up in R and not show up here. Yeah.
So where is it, like really quick, where it says like it's on A, B, C, D, E?
Yeah.
So say that E wasn't there, would the reflexive and transitive be the exact same?
Yes. So if E wasn't here, then the only thing that would change, at least for this problem, would be getting rid of this E here.
Yeah. Okay.
Anyone else? Why is the E missing here? Yeah.
Because R is symmetric.
Yes, but that still doesn't really tell us. Yeah. So again, it kind of has to do with the absence of E. Right? If E is not in any of these, then it can't show up anywhere in here. But E could still be in here, and we'd still like there could be something in here that has an E in it, and we could still end up with this same transitive closure.
So I think here it might be useful to
Write up the definition.
well, actually to show a graph representation.
Oh, okay.
Because
I'll let you do that.
yeah, so okay, so this is A, B. So this is also the importance of representation. So I always say math is the art of saying the same thing with different words. It's Henry Poincaré. So I'm going to write this the graph representation of this relation. So this says that A goes to B, and also that B goes to A, and that C goes to D, and that D goes to C. So here clearly you can see that E is disconnected, and transitivity, what essentially says is that you can think of a transitive closure as adding everything that you can get to from any given vertex in two edges, right? Because think about it, if we add A to the transitive closure, as we do here, is because A goes to B is one of the elements in the relation, and B goes to A is another one. So actually, you can get the transitive closure just by looking at the graph picture, or by thinking about the graph picture. And if something's disconnected, then, but not only that, like if I had E to A, right? Then it's like Danny said, I would have E in my relation, but there's no way to get to E.
So I
Right.
wouldn't have to add anything. Well, I'd have to add maybe E to B, but I wouldn't have to add anything that gets to E.
Right.
Right? If I had maybe an F in my relation,
Yeah.
and I had something like this,
Mhm.
then neither E nor F would show up in things added to my transitive closure.
Does that make sense? And again, if I have F to E, then if I want to look at the symmetric closure, then I just need to add all the edges, all the tuples corresponding to edges of the stuff that I'm missing for everything to be symmetric. And in this case, it would be adding from E to F.
Yeah.
That's
so
the
that would
only
be-
thing I would be missing. Yeah.
That would be for symmetry.
Yeah, and if for reflexivity, it would be everything would
Transitivity.
need, for reflexivity, everything would need an edge to itself.
Yes.
So sometimes it's useful to think about it in these ways. And if you have some time in the exam, you can do, oh, I'm sorry, I think I saw your hand earlier. Yeah. Because that's what's specified by the tuples in the relation, right?
Yeah.
So you can read this as saying A to B. Like A is related to B in a directed way. So we put this directed graph representation.
Yeah.
Yeah.
And then as far as the transitive part goes, so if I've got, let's just focus on just the A and B part in sort of a graph form, and then I'll also write it out in terms of the definition. But if we have just thinking about A and B, right? Now, I can follow two edges on A and B, right? I can start at A, and I can go to B, and then go back to A. So if I think about transitivity, it's the idea of being able to follow two edges and still have an edge that gets me to where I ended up, right? Converting two edges into one edge. So if I take two edges, go to B, and then come back to A, I now need one edge that takes me from A to A. It would look like that. And I can do the same thing starting at B. I can start at B and go to A and come back to B, but I have to be able to do that then in one edge. So that's why AA and ZB show up. We can also look at this in sort of terms of the definition for transitivity. So in general, transitivity says if I've got three elements, A, B, and C, that come from my set, then I can sort of mush things together. I can say if A is related to B and B is related to C, then A has to be related to C. So in this sense, our A's, B's, and C's get slightly confused because what I have is that A is related to B and B is related to A. So now my A and my C are the same, which tells me that A has to be related to A. And a similar thing happens if I start at B. So two different sorts of ways to see where those points go. And the same thing happens with C and D because they have the same structure here, here. Does that all make sense? I know I see you can. Figure I'll take questions in the room first. All right, yeah.
For the transitive one, how would that change if we had BC in the relation?
So if we had BC in the relation, like this, that point. Yeah. So if we did that, then BC does a particular order. So at least I think about this as in terms of our definition here. So we'd have to have a B here in our second spot, or a C. So we'd either have to have the B here and here, right? And have our BC be our second pair. Or we could have a C in the middle with BRC and CR something. Right? So those would be the only two situations where that point would start to become relevant. So in the first, or I guess the one I've written up here, if I've got BRC and CR something, what's my only option now for C to be related to? Well, technically I've got two, but only one that actually makes any difference. Yeah? Yeah. So the only thing that actually does anything new, I could put a C there, but that doesn't actually do anything new. It just leaves me with BC again. But if I put the D here, poor phrasing maybe. If we have C relates to D here, then it gives us something new because B has to relate to D. So that would give us something new. And something similar would happen with using BC as the second part. And then we have to go back and check that this new point BD doesn't add anything new that introduces more transitive situations. So it starts to get kind of iterative in a sense, or you can think about checking recursively, in that once I come up with something new that isn't one of these nice reflexive pairs that keeps everything that function as an identity of sorts with transitivity, in the sense that they don't give us anything new really, but BD might give us, again, something new that I have to play around with and see what can match up with what. And so once we start to introduce more things, then transitivity starts to sort of grow bigger and bigger and bigger and build on itself. So that's part of why this is so small and so contained, is because otherwise the transitive closure would start to explode. So good question, but I'm gonna stop there. Do you have another one?
Yes. Can you explain one more time why it's important to do symmetric closure first or the transitive?
Yeah, so in general, I like to do symmetry before transitivity because sometimes knowing something is symmetric can help you prove that it's transitive. With the closures, it doesn't matter quite so much. But when you're proving something's an equivalence relation, that's when it really comes up and comes in handy. And so I just like to think about these properties in that order all the time. That's why I swapped the order when I was talking about them here. Doesn't help you so much in this situation, but I think it's in one of the bonus problems that the write-up that is on Canvas for the answer actually does exactly that. It makes use of the fact that something is symmetric in order to prove very easily that it's transitive, whereas you'd have to go through more work if you did transitive first and then symmetric. So it will still work out in the end because symmetry does in fact work if you can prove it. So if you can prove symmetry and then use it, you could essentially run through your proof of symmetry at the point where you need to use it in your transitive argument, but it makes your argument easier and cleaner if you prove symmetry first and then just reference the fact that it's symmetric. Another one?
Yes. Does the transitive have BB and DD?
Yeah, so that comes from sort of, I guess I'll reference the graph idea. That comes from being able to go in both directions. So I can start at A and take one edge over to B and take a second edge back to A. And so that gives me AA because I have to then be able to get from A to A with just one edge. But I could also start at B. And I could take B, I could take one edge and get to A, and take one edge and get back to B. And so now I have to be able to get from B to B with just one edge. So I have to include B as a pair in my relation. Any others that come up? Anything else before we move on to the last part of this problem? We're still not done yet.
Oh my gosh. I'll do the next two if you want to.
Sure, yeah, we can do that. Whatever you'd like. All right, so the last part then asks us sort of two questions. It says, first, is the reflexive transitive symmetric closure of R an equivalence? And what it means by equivalence here is equivalence relation. Mathematicians tend to leave off the word relation when we talk about equivalences, because that's sort of our end goal with equivalence relations, is to create an equivalence. So we talk about it in terms of an equivalence as opposed to in terms of a relation. All right, this part's a yes or no question. The closure that is reflexive, transitive, and symmetric going to be an equivalence relation. I see some nods. It is, and it's sort of in the name, right? Because an equivalence relation needs to have those three properties. And a reflexive, transitive, symmetric closure is going to be the smallest superset that has all three of those properties. So it's sort of in the name there that even in general, it's always going to be the case that it's an equivalence relation. In particular with this question, it happens to be the case that's also just the reflexive closure, because everything that we need in the transitive closure, we get it from the reflexive closure, and we don't need anything from the symmetric closure, because all of these pairs are already symmetric. So if we had something like a BC, then it would throw something in a wrench in terms of symmetry, which transitivity might then pick up on and require you to have more things. So requiring multiple properties can sometimes also snowball in the way that just the transitive closure can kind of snowball if we have things that aren't sort of crafted pretty well. But in this case, it happens that because these two are very well behaved, this one ends up being our entire transitive reflexive symmetric closure. So we can see this is an equivalence relation just like it should be. So yes answers that first part. And then the second part of the question says, if so, give the equivalence classes. So I will give myself a little more space here, because that's the only closure we really have to reference. So what would be the equivalence class of A in this problem? A is always going to have an equivalence class. What would be in the equivalence class of A? Yeah, so everything's always going to be in its own equivalence class because it's reflexive, and we can only talk about equivalence classes once we have an equivalence relation. So it's got to be reflexive, so it's always going to have itself. And B, because B is related to A, and A is related to B, and that's the only thing those two are related to, right? B is related to itself and to A is related to itself and to B. There's nothing else that either of them are related to. So that's the equivalence class of A. It's also, I see your hand, one sec, the equivalence class of B. Okay, that's supposed to pass. Yeah. So I like to think about it as the equivalence class of A first, because at this point, I don't know yet what the whole equivalence class is going to be. It might be the case that it's just A, right? So I want to start by picking something, finding its equivalence class. And then I want to pick something whose equivalence class I haven't yet found, find its equivalence class. And then pick something that isn't in either of the previous two equivalence classes. And I keep going like that until I've exhausted all of my options. And that will give me all of my equivalence classes.
You can also look at the 3D graph picture if you're visually inclined.
Yeah,
It's-
the connected components.
Exactly. So if we have the picture, remember, this was our relation. So you see the draw.
Yeah.
So this is our relation.
And
And
the closure.
yeah, and if we do the closure, then really we just need to add the reflexive pairs. And then after that, you just look at the partition that this makes, all the connected components. Voila.
Yes. So that would tell us C and D match up here. The equivalence class of B and the equivalence class of C are the same. And then we've got E on its own. The equivalence class of E is just E. So one thing I'll note is we've got this nice notation for equivalence classes. Unfortunately, it doesn't actually convey all of the information. So if you want to tell us you actually know what is contained in the equivalence classes, your answer would need to be this, or this, where you show what the equal equivalence classes are. If you just gave us this, then that doesn't tell us you know where B and D can actually go.
Don't give us just a representative of each class.
Yeah.
Give us the whole specification.
You need to use more terminology. ACE, like this, would be what we call a complete set of representatives, because it's got sort of one element from each equivalence class. You could think about this sort of like with integers, how I let 10 represent the idea of 10, as opposed to having 10 and 8 plus 2 and 7 plus 3 and 6 plus 4 all present as integers. I just let 10 be the representative for the class of integers and sums that equals 10. Right? So I could think about that in this perspective, which is not what we want for this problem. I want to know that you can put all of these together. And either including all of these, including these equivalences, or listing out the sets is what tells me that you can put all of those together. All right, any last questions before we go back to Mario?
Danny, real quick.
Yes.
Would it be incorrect to state, for example, the equivalence class of B is BA?
That would be fine because these are sets. And so we can switch our order around there. But it would not be the case that I would want to put the equivalence class of D equals BA. That would be wrong. It's only A and B to have the BA equivalence. Yeah, more children. All right. Any last questions while Mario's drawing up his tree? Yes.
So how would we check the transitive symmetric closure of R's?
So there's not very much checking to do because it has all the required properties. So you could really quickly write a proof that it's reflexive because it's a reflexive closure and therefore it's reflexive. It is symmetric because it's also a symmetric closure and therefore it's symmetric. And it's transitive because it's also a transitive closure and therefore it's transitive. So in general, regardless of what the relation R is, if you've got a reflexive, transitive, symmetric closure of it, that's always going to be an equivalence relation. So there's not a whole lot to check per se. But it is worth at least thinking about why that all happens. And it's because all three of those properties are mentioned as properties of the closure and not just one of them. Okay, any other Zoom questions? All right, cool. I will face this. It's a lot of people are there. That one. Okay. Yeah, let's stay over here so I don't walk there.
All right, so now we're gonna move into the part of the exam that starts talking about trees. And it's a little bit unfortunate that trees was like what's covered in the last week. It'd be great to have a little bit more time.
Yeah.
But it's also not such a difficult concept. There's a few problems that are basically free and easy points because they just require that you know the language of trees. Some vocabulary basically.
And I think I mentioned this in the last review session, but definitions and theorems are really great things to include on your cheat sheets. So that if you come across a piece of vocab or jargon that is used on the exam that you don't have committed to memory, if you've got it on your cheat sheet, then you can still work with it. If you haven't put definitions on your cheat sheet, then you're sort of stuck if you don't know what the definition of a piece of jargon is.
Cool. So this one says consider the rooted tree T. Now, this is important. I don't think it'll be tested, but you don't need to have a rooted tree. We might give you a tree, or we might give you a simple connected graph with no simple circuits that doesn't have a clear root, and then we might ask you, is this a tree or not? So you should know that a tree does not necessarily have a root. That's why we use the specification specifically rooted tree. Just keep that in mind. I don't
Yeah.
think we'll test you on that, but you never know.
It's worth noting that you can pick any vertex on a tree to be the root and you will still get a tree. So that's why we sometimes specify which root we're talking about,
Yeah.
because it can be a tree rooted at any one of the vertices drawn up on the board right now, and it will still be a tree.
Yeah.
Now it would be a slightly different tree based on where the root is, but it
It
would
wouldn't-
always still be a tree.
It wouldn't look like a tree, but again, this is just an arbitrary drawing. Like
Yeah.
I could like reorganize everything and then make it look like a tree with a prettier root at the top.
Yeah.
Okay, so the first question says, list the ancestors of A5. A5 is this guy over here. So one thing that's important about trees is that once you have a root, to any given vertex of the tree, there exists a single unique path from the root up to that vertex. So the idea of an ancestor list exploits that fact. So the ancestors of a given vertex will be all of the vertices on the path from the root up to that vertex, not including that vertex. Some of you have come to me and said that their CS professors like to list the vertex itself as the ancestor in the ancestor list. I mean, I don't know. I'm not my own ancestor. I don't know how that makes sense to me. And I've never seen a math textbook that says that, or a computer science textbook for that matter, that calls the ancestor, the vertex itself, as one of its ancestors. But I don't know. Maybe, I don't know.
It's also worth noting, sometimes we as mathematicians do things that aren't technically the definition for clarity.
Yeah.
So for example, when we'll talk later about circuits. I like to include the starting vertex of the circuit also as the ending vertex to make it clear that the path starts and ends at itself. That's not always necessarily how it's done. So sometimes things like that will happen for clarity, even if they don't perfectly match the definition. So you can sort of look out for that too.
Yeah, but we have one textbook, and that one is like the word of God in this class. So
Yeah.
the textbook says that we don't include the ancestor itself. So very simply, we just follow from the root, including the root as an ancestor. So we just write A1 and then B2. Again, this is like brain dead points. If you all you need to do is understand the definition and not get confused. The next one is also pretty easy, and it says, give the height of the tree in a vertex with that level. The height of the tree is defined in terms of the level of vertices. So again, you should write this in your cheat sheet because level has a specific definition. And the level of a vertex is the number of edges in the path from the root. So you can think of it like the ancestor list has all the vertices on the path, and the level of the tree is a number of edges on that path. Okay, so for example, the level of A5 will be 2 because you have 2 edges between it and the root.
You can also sort of think about numbering them in that the root is at level 0. And then the next one down is level 1. The next one down is level 2.
Yeah.
The next one down is level 3.
The only thing that you need to be careful when you do that with drawings is that, and you'll probably notice this, is like Sebastian does not draw the graphs in like nice, like they all don't fall
Yeah.
at the same horizontal line, right? On
Yeah.
the same level.
We like
So-
to draw trees like this, but sometimes LaTeX can be real picky and make it hard to do that. So I think that's part of what's happening with some of the graphs. Is that in order to get it to fit nicely, they don't get to be nice and balanced.
He
like
draws these with like latex.
I'm pretty sure they're all with
Oh,
LaTeX.
really?
Yeah. You gave me the LaTeX of one of the copies of the exam, so I'm pretty sure he uses tech for all of it.
Interesting. Okay, there's such a thing as like too much latex. You can just draw it in PaintNet or something. Hey, although yeah, I guess you want to make it look nice and consistent, but you can also do that.
Graphs and tech are picky.
Yep.
Make it easier for you to do.
Yes and no. It's really helpful for typesetting in general. Drawing things like graphs and tables can actually start to get pretty particular and picky. I've done some graphs in LaTeX myself, and you have to specify particular lengths in directions and stuff. And so a lot of the vertices have to be pointed out in terms of their relationship in inches to other vertices, or points or whatever unit you're using.
Yeah,
Um,
it's not.
So
it's
it get-
an art.
higher allows getting sidetracked, developing a system.
Exactly. Yes.
Yeah, and then when you said like the level of inversity is like the number of edges it has, so how would B9 like, oh, that's the height.
Exactly. Well,
Okay.
yeah,
So
you're
like A
one step ahead of
B,
me.
like level.
Mhm. Yes.
Okay.
So one step ahead of me here. Give the height of the tree and a vertex with that level. So the height is defined as the highest level of any vertex in the tree, which of course will be some sort of leaf node. And here, the highest level is 3, because we have the longest path in this tree from the root is of length 3 in terms of edges.
No, not every leaf node will be at the height.
Mhm.
These leaf nodes are at level 2, whereas these leaf nodes are at level 3. So while a vertex at the height will be a leaf node, not every leaf node will have a level of the height.
So give the height of the tree and a vertex at that level, which is very easy. Again, easy points. You can give B9, you can give B10, you can give B11. You have a bunch of options. The next problem says, yeah,
Can you draw an example?
of an unrooted tree. I mean, you can just grab a tree and say there's no root.
Yeah, so
Yes.
any tree can be an unrooted tree. So this is a perfectly good visual representation of an unrooted tree. It just so happens that we've also specified it's rooted at A1.
Yeah.
It could be rooted at V9, and we could still draw it like this, although I probably wouldn't if it was rooted at V9. But you could. And so any one of those vertices can function as the root, and you will still have a tree.
This would
But,
be
yeah.
an example, for example, because this is a simple connected graph with no simple circles.
Yeah.
And that's what a tree is.
Yeah, so this is also a tree, and again, any single vertex on here can function as the root. You just have to determine which vertex you want the root to be. And usually when we draw trees, we put the root up at the top on its own.
Yeah.
But we don't.
That's the convention.
Yeah.
Just to make it easier for our 8th grades.
Yeah.
Okay, so give the pre-ordered traversal of T. So now is where things start getting a little bit hairy. There's a bunch of ways to traverse trees. Pre-ordered traversal is a simple recursive instruction on how to traverse a tree. And I like to just, really, it's just this simple, especially in a binary tree. You go to the root first, then you explore the left subtree, the first subtree in terms of ordering, and then the second subtree. And then within each of these, you carry out the same routine. So how does that work? And I'll give you an example here, and then I'll give you a little drawing that makes this easier. And actually, I'll do that in the next one. Okay, R, T1, T2. So if what we want to do is like write down in this order, and let me show you how that works. So I'm going to do it up here, just to not have to constantly go there. So I'm going to say C. Okay, so root. So I write down the root, and then I'm going to write a bunch of stuff that's going to be on this subtree, and then a bunch of stuff that's going to be on the other subtree. Okay, so A1, and then I explore the subtree. So what now? Same routine. I grab the root of this subtree, which is B2. And then what next? I need to explore this entire subtree. Okay, I proceed recursively again. Root, subtree, subtree. In this case, it's nice because these subtrees are just have one vertex, so it's super simple. So I do root, which is A4, and then subtree B9, subtree B10. B9, B10. Okay, now I explore this entire subtree. Now I move to the other subtree on the right of A1. Oh, never mind. Oh, sorry. One more recursive. I skipped the recursive level in the stack. So now I do A5. A5 is a root, and then I explore the left subtree. But there's only one subtree, so very easily it'll be A5, B11.
When there's only one subtree, you can sort of decide whether you want it to be the left one or the right one. It won't make a difference.
Yeah.
Yeah.
And then on the right, we do the same. That will be B3 on the root. And then we do all of the other subtrees, B6, B7, B8.
We go left to right. we usually do this in terms of just two things because most of the time we're searching binary trees. But you can expand this, extrapolate to however many children sort of you have. And so when we've got differing numbers of children, we sort of just let it be a little bit arbitrary and go left to right wherever we need to.
One thing that might be helpful, I think, you said Mario.
Yeah, we're just gonna do a drawing example.
Yeah, I was gonna do it for the next problem,
okay.
but the loop trick is pretty good. It's in the book, section something. I don't remember. But it's in the book and it's a nice trick, and I'll explain how that one works. I would say that when you do a visual trick, you also cannot just rely on the visual trick. You need to have some conceptual foundation, and you need to really still understand it. You should use the visual tree as a shortcut, and then you should use your more rigorous analysis to verify that what you wrote was correct. That's at least how I typically perceive it. Okay, so now we go to part D, and this is about like the game trees. So it's actually really cool. I really like this idea of game trees and representing game states as vertices and decisions between players as edges connecting game states. You can think of so many games that you guys enjoy. Like if you enjoy video games, like turn-based games, if you enjoy like trading card games, you can think of it in those terms.
Can I say
Yeah.
one thing about traversals real quick before we
yeah.
jump into game trees?
Yeah.
So sorry to jump back. I wanted to make sure we were done with traversals.
Yeah. We'll come back to it. So.
Yeah, so a quick thing about traversals, something that helps me is to think about these in terms of programs a little bit. So if I've got a very simple tree that is encoding the idea of taking 3 plus 5, then as sort of a human, the way that I would sort of write out a traversal of this tree would want to be 3 plus 5, right? Because that's how we would read it. And this would correspond to taking the left subtree, then the root, then the right subtree. Something that you might have in a computer program, something like Scheme, that is a functional programming language, would be something where it tells you first my function plus, and then my arguments 3 and 5. So this is telling me I'm doing addition and I'm adding 3 and 5 together. And so this would be a traversal like the one we just did, where we start with the root, then we go to the left subtree and then the right subtree. So that's something that helps me a little bit when I'm thinking about what sorts of traversals might be helpful here. Is that this might be the traversal for some kind of functional programming language. This might be the sort of traversal I'd want if I'm sort of going to give it to a human, if I want it to be human readable, right? Because this is going to make much more immediate sense than this. If I've got something stored in a tree and I want to print it out, for example, then I would probably print it out like this, because I want the person that I'm printing it to read it. But if I've got a tree and I want to actually put it into a Scheme program, then I'd want to traverse the tree like this so that it sort of shows up in the order that Scheme wants it to, or any other functional programming language will use a similar order. But that sort of helps me think about these traversals. Postfix traversal, I think, has less of a correlation with these ideas. But it sort of helps me.
That's why I'll introduce the trick for postfix.
It sort of helps me keep these in my head when I think about sort of what situations I would want to be using such traversals and where sort of those would come from. Sorry, you can
No problem.
talk about game trees now.
Yeah. So, okay. So the idea of game trees, again, we can think of each of these vertices as representing a game state and the edges representing decisions connecting game states. And the reason why we label them, we label the levels as a level for A and a level for B and a level for A and so on, is because this is a 2-player game. And this is the state at which A makes a decision. This is the state at which B makes a decision, and A and so on. Now, at the leaf nodes, you have value nodes. And because this happens to be a 2-player, 0-sum deterministic game, then we don't need to model the rewards of both players jointly, or rather separately. We can model them jointly with one single number, because if A wants to win, you can think of A having a score that it wants to maximize, such as, like, for example, if you have a simple rewards function as +1 A wins, -1 A loses, then you can think of the entire game as A trying to say, hey, I want to maximize my reward function. I want to win. I want that score to be +1. Whereas B will say, well, I want to win. I want to win. But because it's a zero-sum two-player game, if for me to win, it is sufficient for A to lose. So that is why we call this min-max algorithm of like propagating the final reward. You can think of these as like the conclusions of the game. And at the end of the game, we assign scores to the end result. So for example,
Really quickly, I will say, you don't always have players that are like doing their best to win. You might have
Yeah.
a player who says, I'm going to randomly make my moves,
yes,
or I'm going to try to make really bad moves.
yes,
So usually we specify what kinds of players we have. The practice exam didn't do this, which irked me a little. It didn't specify what sort of players we had. So Mario described what we would call usually optimal players or players making optimal decisions, which is also what the answer key assumed we had.
imagine like a very competitive try hard.
Yeah.
Right? It's just like
Players
trying
who are
to
like
isolate.
professional players who
Yeah.
are at the top of their game, who can always do the best, make the best move when there's an option. But you can have anything from totally random to totally bad to totally good to anything in between. Maybe you've got a chance to be good or a chance to be random.
And that assumes, of course, that you know the optimal policy. Policy
Yes.
is like the function that you have, and all of you have policies for games. A policy is a function that essentially maps state action pairs to
Essentially, you take in all the
distribution.
information about the game state
yeah.
and you use some of it to determine what your move is going to be.
Right.
And so
Mhm.
a random player might take in all that information and then randomly choose a path.
Yeah.
A optimal player might take in all that information and run calculations and computations about what will happen if I make these different moves.
Yes. I know we're getting a little bit past Seaside 2011, but this is interesting stuff. And if you take 4511W, Introduction to Artificial Intelligence, you get to see a lot of this. You might even do a project on this, and that'll be pretty fun. And then you also might have me as your TA, because I like the TA that class, and I usually I've TA'd a bunch of stuff. Yeah.
So
Well,
I'm gonna
assume-
make sure I'm gonna pester Sebastian into if he asks about game trees, being specific about the kind of players. I assumed random when I first went through this. When I first went through the practice exam. Some people might assume optimal decisions. So if it's not specified on the exam, just write a sentence saying what kind of players you're expecting.
Yeah.
If you're expecting usually it would be optimal or random would be the reasonable choices for this exam. I wouldn't want like 25% optimal, 25% suboptimal, and 50% random.
Yeah.
Like it wouldn't be sort of practical for the exam to assume that. So I would assume either optimal or random, and tell us what you assume if it's not specified. But again, I'm gonna try to pester Sebastian into making sure he specifies.
You can think of just one last example, in this example of a policy and a game tree. You can think of tic-tac-toe. For tic-tac-toe, there's very clearly an optimal policy. I think we all learned that pretty quickly, like in elementary school, right?
Yeah.
For other games, you don't have an optimal policy that's so obvious. There might be one. Sometimes the optimal policy is not even like clear in terms of like what decision to make every time. Sometimes it's a probability distribution over decisions. So you have to like, with such probability, this is the right decision or the best decision. So
Sometimes you have to take into account your opponent. For example, in chess, if you're playing against an amateur versus a professional, your opponent is going to be making different kinds of decisions. And so your decisions would have to take into account what kinds of decisions they are likely to make.
some players that get really good at a specific game sometimes have trouble beating lower skill players because they're so used to the opponent playing near optimally.
Yeah.
So that's actually something that happens sometimes. In
And
games.
then the opponent does something suboptimal and it
Yeah.
throws off their strategy.
Yeah.
Kind of cool.
Nani.
Yeah, it's really fun actually to look at some examples of that.
Okay, so
We're
back
off
to the
track
problem.
again.
Back to the problem. So let's think about it now that we have some rudimentary understanding of this game thing. So if A4 is making a decision to get to one of these final states, A4 wants to win. It's just as simple as thinking about it in those terms. A4 wants to win. So if it has to make a decision and we have to propagate that value upwards to carry out all the way to the root, do you think it's going to pick B9 or B10? B9, because it wants to maximize its score. So we're going to say that the value of this node is going to be +1. Now, A5 could also get to this game state, and in which case it'll only have one decision, and it wants to win, but there's nothing else it can do. And luckily for him, this is a +1. So we propagate the +1 upwards. Now, B2, B2 in this instance, B2 wants A to lose, but unluckily for B, both of these states are favorable for A. So even though it would try to select the lowest reward for A, the lowest reward is still a situation in which A wins. So we propagate the +1 upwards. Now, in this instance, B3 can make a decision that will lead to this end state in which A loses, and also this end state in which A loses. So if he has to make decisions between these three, he'll pick any of these that makes A lose. So then the reward that we propagate upwards is -1. But then at the very top of the game, and you can think of it, it's not like the decisions are made from the bottom up. You can think of this as like this is the beginning of the game, and A does like Doctor Strange in Endgame, and like looks at all the possible universes and then chooses the best course of action, right? So then it does A1. Okay, well, if I go down this route, I'm guaranteed to win. But if I go down this route, I'm guaranteed to lose if B plays optimal. So I'm just going to do +1. So the winner is A. And that's it. It's as simple as this.
So this question gets a little more complicated if you look at a random opponent, in that A5 here is actually going to be the only node with a guaranteed outcome. This one, A wins. But over here, if A is playing randomly, either one of these could happen. Here, if B is still also playing randomly, either one of these could happen.
Yeah.
But since this was random, we don't actually know the outcome here. So we can't know the outcome here. If, for example, maybe A is playing optimally, but B is playing randomly, then we'd still have +1 here and +1 here. So it doesn't matter what B does, B can pick randomly and we'll get +1. So you get some sort of interesting interactions if you have random opponents. And so it's worth noting that in case Sebastian wants us to have random opponents in a game.
Can we look at that in lecture?
I don't know, but I always assume random moves unless otherwise specified in a game tree. So
If I
that
were
would be a
you,
thought
if it's
process.
not specified, I would probably assume optimal play.
Optimal play will probably be easier
Yeah.
for you, so that could be a good strategy. But again, I'm
Exactly.
going to do my best to make sure Sebastian actually says what he wants. There's also a problem where I'm going to pester Sebastian into specifying, because he doesn't say whether or not we're supposed to use order of operations. That changes this answer.
Yes. So we consider the following expression. This is exercise 6. So this gives us A and B. Now, this is where you want to have your big brain moment and read the entire problem before you solve it. Because if you look at part A and you know how to write postfix only with the expression tree, you might want to do B first. You write the expression tree and then you navigate that in post order to get your postfix answer. So that's what I'm going to do here. Now, you can also learn how to read postfix or how to write postfix from a mathematical expression. And it's not so difficult. It's similar to what Danny was showing here. Now, we can walk through an example of that also. But let me first draw the expression tree. So I'm going to do what Danny did with that very, very simple expression tree where they had 3 + 5. And I'm going to do that, but now I have a composite expression, right? I'm composing a lot of binary operators. Luckily, I don't think there's no unary operator here, but keep in mind, there might be a unary operator, right? If I had like this, then I'm going to have a tree here, right? I don't know what it's going to look like yet because I haven't done it. But if I had a unary operator here, then this would be like that. I would have like a minus and then the entire tree. So just keep that in mind. We haven't seen any examples of this, right? I don't think there's examples of unary in the homework that I remember, but it is a thing.
You could theoretically treat exponentiation as unary. You could also treat it as a exponentiation as a variable number of things or nested things. Exponentiation could get complicated.
Yeah.
So you could have it as a unary by putting the exponent and having one child. You could think about it as being nested in that you're sort of grouping together a bunch of multiplications. Or you could think about it as having sort of a variable number of children, in that maybe something to the third power has 3 children, while something squared has 2 children. So you could think about it in different
You can
ways.
also think of subtraction as this.
Yeah.
I guess technically, I don't know. I mean, there's many ways of representing it. I personally, if I'm grading this, I just care that you know how to.
Yeah, if you sort of pick something that makes sense, so I would take, for example, exponentiation, I would take any of the three things I just described as a valid way to put exponentiation into a tree. Right, if you do something that makes sense, we're gonna try to give you points for it.
So in order to begin solving this, you sort of need to parse out the structure of this, and we're going to write a binary tree. So we need to think of all this expression, this composite expression, in terms of like operations joining compositions of other operations. So note that in some cases like this, you might notice that at the top level, we have this, and then subtracting this and adding this. And we know a thing or two about order of operations and commutativity. So sometimes you will have choices as to how you want to group things up and associate things. In this case, just to make things very, very simple, I'm going to do it like this, where I'm going to have, this is going to be my top level operation. This is going to be one subtree, and this is going to be another subtree. And then we can kind of proceed recursively just by looking at this and parsing the structure of it. So for example, I have another operation here, and then I'm going to have this, and I'm going to have this. Probably should have done it like that first.
If you want to do this at the highest level, like Mario's doing, I recommend putting in every single set of parentheses and grouping signs, because that will tell you where to split into trees and where to sort of have a complete tree intact. That is why this question is different if we use order of operations or not, because if we don't use order of operations, then we have that 3 and 5 get split in trees. Whereas if we use order of operations, these are grouped together because it's multiplication, and so they get put into the same subtree. So put in your parentheses, and that will very much help you determine how your tree structure will look.
Yeah. Put you in parentheses. You can also do this. I just came up with this, but I think it's also a good way to kind of visually parse this structure. So kind of like this. So let's start writing out our tree. So I have the plus. And then I will have the left subtree and the right subtree. So the right subtree, luckily, is just going to be a simple one. But the left subtree is going to be this complicated thing. So now I need to look at the next top level operation in this case. Oh, yep.
Are left and right interchangeable, or it matters, right?
That's a good question. You should try to have a consistent order because there are operators, right, such as subtraction and division that are not symmetric. So I would say that the order does matter. And
because we've specified a traversal order in the problem, we want to have this we want to have the structure of the tree mimicking the orders of the operators here. So we want 15 times 2 times 4 to have 15 on the left and 2 times 4 on the right, because we've defined a dot as multiplication, which could switch order. But this dot could become some other kind of operator that does care about order. And so we want to preserve the order for that operator if we defined it to be something else.
Yeah, 15 minus, like, that was like
Yeah.
minus 15 minus 8 is 11.
yeah, another way to think about it is forget the fact that these are math symbols and just think about it like some arbitrary widgets that have their own rules.
I've seen professors do something like that where they use like smiley faces as operators. So
Keel. Jordan, what's his name? Marcus Keel? Is that him?
I don't know.
Oh, Marcus Keel. He's interesting professor. Yeah. Well, what I would say is try to make sure that you don't change the expression when you associate them, right? Like if you group it like this minus this, then you will be changing the mathematical value of the expression because the minus will be distributing with the plus.
So we tend to think about subtraction and addition having sort of the same level of importance. And so you just work left to right, which tells us we do the subtraction before we do the addition. And so that tells us, in essence, the addition happens last. So we're adding the 1 into this whole rest of it. If you think about PEMDAS, technically that puts addition before subtraction. And so you could have a justification for doing the other grouping. But we'd like to usually think about addition and subtraction having the same priority. So we just work left to right.
Okay, so let's continue with our expression tree. So now we're in this subtree, and the top level operator, the one that's not in any brackets. You can think of it like that if you opt to do it in this with this visual whatever.
Style.
Yeah, this thing I just came up with. This is a nice thing. You can come up with all these things that as long as you preserve the importance of the computation, it's fine.
Whatever makes it make sense to you.
Mhm. So we go next subtraction and then left subtree, right subtree. So we're gonna have left subtree, right subtree. Okay, I'm gonna do left subtree and then I'm gonna worry about this one. What is the top level operation? I look what is at this parentheses, this is the top level operation. So I'm gonna do that. And now I'm gonna do left subtree 15, right subtree, another top level operation, which in this case is this. It's the one that's at that level in the parentheses, which is erased. And then 2 and 4. 2, 4. And then we have one last subtree that we haven't touched, which is this one. So we do again, top level operation, and then 3 and 5. So probably one of the worst trees I've ever drawn.
It gets the point across.
There you go. Okay, so now we have our expression tree. And just like Danny showed that we can do pre-order traversal to write a prefix notation, we can do post-order traversal to write postfix notation. I'm going to do both because I want to show this visual method that's in the book. Yeah. If you have the minus as the root node, look at what happens. I would have, I guess not.
It's got black markers.
I will have this and this. There's a lot of brackets now, so it's kind of hard to see. But if I subtract this, if I do like minus and then parentheses, 3.3 times 5 plus 1, you know distribution, right? So it would be like you would distribute the minus and you would effectively be subtracting the 1. So you're actually changing the mathematical operation that you're computing.
So you will end up with a different value. As I mentioned earlier, there is an argument to be made if you're thinking about using PEMDAS in particular, that addition could be thought of as coming before subtraction, in which case you would want subtraction to be your sort of highest level operator because you want to do that last. And you can think about sort of going up the tree, and the last thing you would want to do is subtraction. And so subtraction would be sort of at your highest level. However, we tend to think usually about addition and subtraction, much like multiplication and division, being at the same level of importance. And in that situation, we work left to right. So most of us would think about having sort of the addition of the plus being the last thing we do, right? And if we actually solved through this, I think most of us would add in the 1 at the end and not distribute the negative and subtract at the end. So that's how we would normally sort of split it up, but there is an argument to be made about a correct answer that has the minus.
Yeah. So I'm going to show you the trick, and this is in the book. If you don't remember this, or if the explanation that's recorded on video or that you see right now is not sufficient for you, you can find it in the book. I can't remember the specific section, but it's the section that talks about pre-order and post-order traversal. So you can find it. So this trick is cool. Essentially, if you want to find the pre-order or post-order traversal, you first just draw this, I don't know, this membrane or something around the tree. You just draw this curve that goes and curves all around the tree. And then you can think of you following this curve in a counterclockwise direction, right? You start to the left, towards going to the left. And then you can find the pre-order and the post-order traversal very easily. Essentially, for pre-order, the way you find the pre-order traversal is whenever you pass the node the first time, when you go down, you write down the value. So if I pass a node, like imagine that each node has like a sort of like a horizontal line by the middle. It's like, okay, if I cross that line once as I'm going down, I'm gonna write that node. So let's see what that looks like. So if I start and I go down, I cross that line for this one, plus, I saw that guy, and it's plus. And then I keep going down, and now I see the minus, so I write minus. And I keep going down, and it's like, oh, now I passed by the multiplication. You can probably write it a little bit tighter to the tree, so it's easier to see, right? Now multiplication, and then 15. And then now I keep going, now I go back up, and now product again. And now go and 2, and then 4, as you can see if you follow. So I'm just going to speed up a little bit. And now I go here, and I already wrote this multiplication. And then go keep down, 3. And then I go 5. And then I already wrote all those guys, and then 1, and I'm done. Pre-order traversal, pretty simple. You just follow the curve with your eyes. Now for post-order traversal, it's a little bit trickier. So the specification, if for pre-order traversal, the specification was root subtree 1 or left subtree, right subtree. For post-order traversal is left subtree, right subtree, and root at the end. And this is a little bad for us, at least for some of us. It's bad for me. I'm used to from reading to left to right.
It's backwards for me also.
Mhm.
That's why I didn't have a handy sort of correlation to this sort of traversal when I was talking earlier.
Yeah, it's tricky. It's much tricky because think about it, right? Like if I follow this curve visually, most of us go like up, down, left, right, if we're looking at this tree structure. I don't know how much of it is a cultural bias of us like reading left,
Some
right.
of it is reading cultural bias,
Yeah,
and some of it is right-handed bias as well.
yeah. So we have this cognitive biases, that some of them are cultural. And I don't know, it's just hard. What can I say? But if we do this trick, it's going to be nice. So let me just say what this would look like if we try to do it like the normal way. I want to traverse, but I look at this node, right? But I don't write it yet. I first need to look at this entire subtree and then this entire subtree and write all of that before I can even write this one. And when I proceed recursively and I go here, I need to look at this entire subtree and this entire subtree before I go this one. So it needs some like additional mental bookkeeping that sometimes it's kind of hard to do. But if you do this method with the curve, and again, I would suggest that if you do this method, you need to understand how to do it this way. You should verify that the thing that you write down follows this recursive instruction structure. Okay, so how does this work compared to this one? If for pre-order, we wrote the node as soon as we crossed it the first time going down, for post-order, we write it the second time we cross it going up. And for that, you should try to make sure that your curve hugs the tree as tight as possible to make that easy for you to see. So I'll show you what this looks like. So then we go down the curve and I cross the plus. In pre-order, I would write it down, but in post-order, I don't write it down. I'm going to write it down when I come back up all the way after.
I like to think about this as the first upward crossing as opposed to the second crossing that also goes up. Either way works, whatever kind of makes more sense to you.
Yeah. So find the way it makes more sense to you. I keep going down and now I cross the minus, but I'm not writing it yet. I keep going down, I cross the multiplication, not writing it yet. I keep going down 15, I don't write it yet. Then I curve upwards and now I am crossing it for the second time when I go up. And now I write it, I write 15. Okay, and then I go up and I don't write anything, I don't write anything, I don't write anything. Aha, I cross the 2 the second time going up. So I write 2. And then I go back down and here I cross the 4 going up, 4. And I go back up and here I cross the multiplication sign going up. And I keep going up and I cross the other multiplication sign going up. And then I curve back down and I curve around the 3 and then I cross the 3 going up. So I write the 3 and then I go back down to 5. I cross the 5 going up. You get the idea, right? And now it's pretty simple. I just write this multiplication 2 and I keep going up. I curve around. I write the 1. Oh, I forgot the subtraction. Multiplication, subtraction, and then the 1. Thank you. And then the plus. And that's it. And this is your post-order solution. Someone can check that he did it right. He did it. 15, 2, 4, ... 3, 5, ... -1 plus. Yep,
Yep.
So that's it. That's your answer.
And your tree matches up with E too.
So if we were, and this is the pre-order version, this is the post-order version. It's pretty simple. Okay, so that's this problem. We're almost done. We got 3 problems, but the last one is so simple. So we really only got 2 problems. Yeah, what's up?
Must have just means, which one is the most?
Oh, the second one. Yeah, this is the one I was just writing in this method. And again, look at the book, consult with the book to make sure that you're doing it the right way.
Yep.
Here. So you, again, it's the same, you follow the same path. The difference is when you print the node value. You print it when you go up, curving around the node. That's the only difference. And for pre-order, the first time. For post-order, the second time. If this wasn't 100% clear, like please look at the book. And because you have your notes, right, for the exam. So you can like grab a little picture from the book and make your own little summary there. So yeah, let me erase this for you. No. I can handle that.
You want to talk about 8? You did such a good write up for it.
Yeah, I can talk about age.
Then I can take 7 and 9.
Yeah, 9 is so short. 9 is free.
Yeah.
All right, so for question 7, we've got a graph here, and it wants to know what is the highest number of edges a spanning tree of G can have. So what does a spanning tree have to do first off? How does a spanning tree work? So we need to know what spanning tree works in order to figure out this question.
That's to look at every vertex.
Yeah, so spanning tree starts somewhere and then is a tree that connects all of the vertices. Right? So you have to have a connected graph for that, which luckily we do. So we can actually have a spanning tree. And so now any spanning tree can start anywhere. And because it's connected, it will be able to create a spanning tree. Right? As we mentioned, any tree you can sort of change your roots around. Right? So you could pick, if there is going to be a spanning tree, you could pick any vertex and use that to create a spanning tree. But depending on what tree you actually create, the height of the tree is going to be different based on where the root is. Right? So how would we go about sort of creating a spanning tree that has as much height as possible? Anyone? Good hand? Yeah.
First.
All right. So we've got depth first search with the Hamilton circuit. All right. And so what would that process look like?
All of the line all the way.
Yeah. So we have to have a Hamilton circuit in order to do that, right? But if we do, then we can have sort of a tree that ends up just being a line, right? If we can do that. If we can't, we've got to do some more calculations. But for this one, we can't, right? So first we have to notice that we can do that. But then once we do, we end up with a tree that just goes like this. And yes.
Are we finding the highest number of edges right now?
We are finding part A. So the spanning tree with the highest number of edges.
Yeah, isn't that just the number of nodes or vertices minus 1?
Yeah, so we can look at that too, right? But we can sort of think about sort of trying to find sort of, I like to think about sort of trying to find something like this, because that's going to maximize not only the number of edges, but also the height.
Yeah.
Which is something we sometimes like to maximize. Right. And so we can think about, we've got 12 vertices, so the internal edges there are going to be 11. Right. So I think it makes it really clear on this sort of graph or this sort of tree how many edges we're going to have. Right. So this gives us 11 edges. We can also sort of think about trees in general, which are going to have one fewer edge than they do vertices. And so we can sort of think about it that way. I like to think about that in a sort of a different way. I like to think about parents and children. Every node has exactly one parent, which means that there's exactly one parent edge from every node except the root. And so we get every node minus one contributes one edge. Right? So we can think about it sort of that way for a general spanning tree. But I like to think about sort of maximizing the height for this problem because it makes it really easy to see all those edges.
Yeah.
All right, so does that make sense for part A? All right, cool. For part B, we want to know if G has an Euler circuit. I know it's spelled Euler, but it's pronounced Euler. Anyway, we want to know if there is an Euler circuit, and if so, we want to give it, and if not, we want to state why it can't happen. So, what do we think? Can we do it? And if not, why?
Like, is it just as simple as like, because, like, if you make a circuit on the graph and stuff, anywhere there's vertex odd degrees.
Yeah, so in fact, the justification in the answer key is exactly, there's at least one odd degree vertex. This is, I think, what it says. Yeah, so it just says there exists a vertex, an odd degree vertex. Right, so it can be sort of, you can get sort of simple, right? You can also have, but that doesn't necessarily mean that's going to be the only way to justify that such a circuit doesn't exist. You could have a disconnected graph that's not going to be able to have certain kinds of circuits, but could have other kinds of circuits. Right, so different sorts of properties of the graphs are going to give you sort of different abilities to justify in different ways, whether or not certain kinds of circuits are going to exist. All right, so we mentioned earlier that there in fact is a Hamilton circuit on this graph. And so we want to give one. And yes. So like if it asked for the path of an Euler circuit.
Look at the after it exists.
Yeah, it's if and only if.
Yeah.
Yes.
Yeah, so like, or if it says, yeah, so like it goes in both directions. So like if it says, so for example, if there isn't an Euler circuit, then there's not going to be a vertex of odd degree. If there is a vertex of odd degree, then there's not going to be an Euler circuit. But I believe just because every vertex has an even degree doesn't guarantee an Euler circuit will be there.
I'm pretty sure there is. I think it's if and only if. I can check. But I'm not sure.
I feel like that also, it would also have to be connected, I think.
Good point.
So you could say something like, if a connected graph has only odd degree vertices, then I might believe you, but I think it would have to have the connected.
I'm gonna try. Yeah.
But double check for me, but I do think it needs that extra specification.
Hi folks, I'm just creeping over here.
All right, so for the Hamilton circuit, we do have one, which means we could, in theory, sort of start anywhere. Where would we like to start?
Okay, a connected multigraph with at least two vertices has an Euler circuit if and only if each of its vertices is an even degree. Yeah.
Okay, yeah, so it needs connected, but yes, if it's connected, then you could look at having all even degrees, and it will work. But it needs that extra specification of being connected, because otherwise you could have a 0 degree vertex that throws everything off.
Yeah.
Or some other partially connected components. All right. So I'm just going to follow where the answer key starts then, because that makes it easy, which is starting at 01. Nobody seems to have opinions. All right. 01, we're going to start up here. And then we want to follow our path around. So where do we think we might want to start? Where would we want to go? O2.
Oh, wait, this is kind of a fun problem too, right? Like some of you play like a Zelda game or something. You've probably done something similar to this.
Yeah, so you can sort of try to play some games with this.
Yeah. I think they should replace Sudokus and crosswords in the newspaper with just graph problems. That's
I love Sudokus, so. All right, where do we want to go now? We want to stay on the outside? Yeah, you're not going to stay on the outside. That's not going to help us, right? So where do we want to go next? I1. So we can go sort of into these internal. Right? So we got to play around a little bit because it might not work right if we go to O3. Right? So we've got to sort of make some decisions here. All right. What do we think? What next? O3? All right. Oh, which one? O4. O4? And now where do we go?
A2.
Okay, I2. Where now? 3. Yep, there's only one option there, right? How about now? We've still got only one option. So we can start to see it coming together a bit. So I'll go a little faster. We're gonna sort of go back to the outside, and then it gives us a series of only one option. So we get 5, 6, and 7 on the O's. Right. So those are all sort of forced. And now, where do we go? We got 2 edges, but only one of them helps us. Well, we've only got one place we haven't visited yet. So we can go to I5. And then we want to finish off our circuit, which has to start and end at the same place. So we go up to O1. That makes sense as to sort of how we go about finding that. But for example, if we just went around the outside and then tried to do the internal nodes, it wouldn't work, right? So we'd have to duplicate edges. I'd have to go across here again. I'd have to turn back around, right? So we have to have a little bit of sort of strategic planning involved in how we put that together. All right. So now we want to use a breadth first search to find a spanning tree of G rooted at I1. There's a lot of words there. So we're going to root here. And we want to find a breadth first search tree. Rooted there. So my root is going to be my first node. And I think it wants us to have, it wants us to draw it out. But the answer key is unhelpful and doesn't actually draw it out. So I'm just going to draw it here without looking at the answer key and hope it matches up. So it's rooted at I1. So I'm going to have I1 be here. For breadth first search, where do I go after I1? Anybody? Yeah. I2. Do we go anywhere else on a breadth first search?
Okay.
Yeah, I heard O2 and O3, which are also both correct answers. Right, so for a breadth first search, we look at all the neighbors before we move on. Right, so I start somewhere, I look at all the neighbors, and then I look at the neighbors of each of those neighbors. So you can think about sort of the levels of the tree. I start at level 0, and I look at all the things that are going to be in level 1 before I move on to anything in level 2. Right? You can also think about like how far away you have to get from the start. I want to start by looking only at things that I can get to by traveling sort of 1 unit of distance, by taking 1 edge. And then I want to look at all the things I can get to by 2 edges. Right? Or in other words, anything that I can get to in 1 edge from this level. And we typically like to work sort of left to right-ish, but it will make for isomorphic trees. There's isomorphisms again. It'll make for isomorphic trees if you switch around left to right orderings, provided you use the same neighbors for each vertex. If you choose to visit a vertex from a different parent, then that would change your tree structure. But if you just switch around sort of the left to right ordering that we write it in, then that won't make any difference. All right. So I2, can one of I2's neighbors that I'm visiting be I1? I can get there in two paths. Why not?
It's already on there.
Yeah, it's already on there. So I just want to look at the unvisited nodes.
I3 and A4.
Yeah, so I3 and O4.
I do want to make a note, when you're expanding a vertex and finding its neighbors, while the order doesn't matter, it does help to have a consistent order, if only for like your own personal bookkeeping.
Yes.
And also, if you write down how you're expanding them, if there's a systematic way, it will help us check your work.
Yeah.
So one way you can do that is, I like to think of like this like clock expansion. So if you're here and you want to write down these neighbors, you think of it like a clock, and then you write them down clockwise.
Yeah. So
That's
you
one way
can
of doing it.
you can sort of do that. That requires you to have a nice drawing, right? So you can sort of do whatever, but yeah, being consistent. I like to usually go, and when I think of it, left to right, or if you've got some sort of numbering on it, I like to go in numerical or alphabetical order on things. But it doesn't really matter all that much as long as you are somewhat consistent for your own bookkeeping. Although you can also be inconsistent and still have an accurate tree, it's just going to make it harder. Yeah.
In the textbook, the answer key goes by numerical order.
That assumes you have a numerical value of the on the node.
Like the 3 and 4. It was
So,
based on
yeah.
this one.
So that assumes that you have some sort of index on your labels for your nodes. I could label nodes via fun little symbols, and I could have like a star and a smiley face and a goofy face and a frowny face and a crying face. And then I can't really impose a particular ordering on whether or not smiley face comes before star. So if I did something like that, then I'd want to figure out, like, am I going to go left to right? Am I going to go clockwise? Am I going to go counterclockwise? Am I just going to sort of randomly pick things? So if you have an ordering, that can be really useful, but you're not necessarily always going to have an ordering with your layers. Now you could relabel your graph to have something orderable. That would work too. But you'd sort of be imposing sort of a randomness by picking a particular ordering when you do that. Does that answer your question?
Yeah.
Right. Cool. So before we visit I3 and O4's neighbors, I go back to O2 and I look at those neighbors. Right now I'm not actually searching for anything in particular, so I'm going to get through everything. But if I was searching for something in particular, even if it was right off of I3, I'd still go back and look at O2 and O3's neighbors before I looked at I3's neighbors. So O2 has these two neighbors that we've already looked at, right? A program would mark those as visited. So O1 is the only neighbor we have left for that. And O3 has, I believe, 0 neighbors that we have not visited. So we can actually sort of end our O3 tree. Stops there, and I no longer have to consider it because I can't get anywhere else from O3 that I haven't already looked at. But here's where the ordering comes in. If I had done O3's neighbors before I2's neighbors, O4 would show up as O3's child, right? So here's where the ordering will make for a consistent graph if you have a consistent ordering. But if someone picks a different ordering than you, they might end up with a different tree. All right. I3 has one child or one neighbor we haven't looked at yet, which is I4. How about O4? Anything we haven't seen yet? Yep. O5. And O1 has, I think, 2 neighbors we haven't seen yet. So we've got O7 and I5. All right, where do we go next? I've been working left to right how I wrote them. Does I4 have anything we need? Yeah. I4 has an unvisited neighbor in 06, but now we should have every node here. So all the rest of these neighbors that we have to look at for these are going to be things we've visited already. Any questions about that? So the last question is, I believe, depth first search with a root node at 01. So there's actually a lot more versatility now in this depth first search, because basically what I'm doing is at every node, I'm picking one of the nodes adjacent to it that I haven't visited yet, and I'm going to go visit that. And then I keep repeating that process. So depending on what I do, it could be the case that I get this straight tree, right? So if you know that, that's an option, then that could be a pretty easy answer for this question, right? So that could be one of those short circuits we've talked about, is I know if I make the right choices, I can have a really easy tree that looks like this, right? Because I've got that Hamilton circuit I can follow. So if I'm sort of thinking about that, then I don't even have to follow anything because I've already got my Hamilton circuit, and so I can just put that into the tree. If I'm sort of trying to think about ways to save time. But I could also sort of go through and be sort of this random choice maker that's going to go through and make random choices at every vertex and put that together into a tree. So let's do that just for the sake of actually going through it, unless people don't want to see that. We can go through and sort of make somewhat arbitrary choices and see what we end up with. So we have to start at 01. Right? Let's say maybe I do start the same way the circuit does. Let's say I go to 02. All right. And then I said, I'm not going to do the same way the circuit does. I'm going to go now to 03. And I said, let's go inside. So let's go to I1. And I don't know anything about potential other children. So I'm just going to sort of draw these straight down and assume I get something that works like that until at some point I have to have other children. So now let's say, let's go with I3. Move that around so it's consistent. All right, 3. Then I4 is my only option. And then let's go to 05. And now I'm going to go to 04. '04 has no more options, right? I've visited everything. Yeah.
Why are you allowed to go from 03 to I?
Oh, did I?
It should be I1 then.
Yes, good point. Dropped in I1. Thank you.
Will the next one have to?
Yes. So 03, I1, I2. Then I3. Thanks for that catch. So now I'm at 04, and I can't go anywhere from 04. Does that mean I'm done? Have I finished my depth first search? No, I haven't. How do I continue from here? So I like to think about this in terms of how we actually implement a depth first search, which uses a stack. I hope some of you at least are familiar with the idea of a stack. And so what we do is we put all of these onto the stack until I get to a point where I can't go any further, and then I pop things off the stack. So essentially I step back one node, and at each point there, I check if there's something I could have explored but didn't. So I said, okay, 04 is now a dead end, because every neighbor of 04 is explored. So I hop back up to 05, and I see if 05 has any unexplored neighbors. Turns out it does. 06 is an option. So I split off at 05, and I go to 06. So now I see if 06 has new options, which it does in terms of 07. And then from 07, I can actually go in either direction and I'll be able to finish this off. Right, I can either go to O1 and then I5 or I5 and then O1, and that should get us to every node. Right? Let's say I stick with the O's first. And then I go down to my last I5. Now I am done. So we can see we don't necessarily have that same nice straight path through that we could have had if we sort of used a trick and just picked the Hamilton circuit. But this is also a perfectly valid depth first search tree. And there's plenty of other ones depending on which choices you make. Although at some point they will probably look somewhat similar to this, and that they'll probably have one, maybe two branches, but there's not a whole lot of actual branching you can do here. It looks like it, but because of the way it's connected, there's not actually a whole lot of options you have in terms of branching. But you might have switched orders more than branching. Yes.
Well, the graph for search tree would it be valid to have 0605, the 5 4?
Yeah, I believe so. Where do we start here? I1, 1, 2, 3, 4. Yes. So yeah, again, it depends on which vertices you choose to look at first. So at each level, you will have the same set of vertices because you will have the ability to get to them in sort of that shortest path of that level. So anything that I can get to from I1 in two edges will be either, if I can only do it with exactly 2 edges, then it will be on level 2. If I can do it with 1 edge or 2 edges, it'll be on level 1, right? And I can do it with 0 edges at the root. So anything that can be gotten to with a sort of minimal path of a certain length will be on that level. Any other questions? Yes.
Going back to the circuits, was the starting point arbitrary?
Yes. So the way that the circuits work, in fact, makes it so that the starting point is arbitrary. If a circuit's going to exist that passes through every vertex, then I can start wherever I would like. I will be able to hit every vertex. If there's a circuit that passes through all the edges, then I can start anywhere on that circuit, and I can create that circuit starting anywhere. If there's a circuit that hits all the edges but doesn't hit all the vertices, then you would have to take a vertex that is on the path with the edges. So for example, if I've got something disconnected that lets me have all of my edges in one place. So if I've got something that looks like here, then I can make a circuit here that hits all the edges, but I could never do it starting at this vertex.
Another way to see it is like the circuit in a graph like this, which is like a tessellation, there's no crossing edges. It will make a polygon. And obviously, if you start at any point here, you can get to, doesn't matter, you can complete the poly, you can follow it along. Another thing you can think about is like, well, what if it doesn't make a tessellation and there's edges that cross? In that case, like, well, you can just find an isomorphism, an isomorphic circuit that is a nice little thing like this, and you could traverse that.
Yeah, so circuits are always going to be able to be done like that.
Yeah.
However, you might not always be able to get rid of all the crossing edges. There are going to be some graphs that no matter what you draw them like, you will have to have at least one crossing edge or at least some number of crossing edges. But if you've got a circuit like that, you can make it so that the path of the circuit doesn't cross. So, or at least you should be able to. So that can also help you. Okay. Anything else before Mario takes over for problem 8? Right. I don't think so. Usually there would be some sort of alarm going along with the noise to kill us.
It's a very annoying noise.
Yeah, it's just annoying. It's not deadly, I think.
Chat, if the noise is too bad, let us know. I don't know.
Also, chat, if you happen to know the noise is deadly, please let us know.
Yeah, please.
Leave the noise. Yeah. That's true. We're in the basement. So if it's a tornado, we're good.
Okay, so for this explanation of exercise 8, I am going to mostly follow what I wrote in pages, but I can do an alternative way probably to show how to do it in some other way. If that way doesn't work with you, there's many ways of doing all these things. So let me draw the graph. We're all a little bit tired, right?
I was getting a little tired.
Yeah.
But we're getting very close to the end. I assume we're not gonna talk about both.
We're so close to the end, and all of you, thank you for making it this far.
Yes. I know it's a pretty big time component. I think also we might save the bonus exercise for specific questions. So if you specifically want to talk about the bonus exercise, I think we'll be happy to do it, but I don't think, at least I don't think it will be as worth our time to go through all of the bonus exercise pieces. So that'll be like a, if it's wanted, we can talk about them sort of deal.
I love math.
Yeah.
Can you draw the yellow one? Because this is like one of the things that takes so long to draw.
Yes, I know. I spent a lot of my discussion time drawing graphs, then erasing them only to draw them again.
I shouldn't have erased that one.
I shouldn't have erased that, but at the same time, I need my word speed. I like to do a loopy L to make it cool.
I'm terrible.
I've been have my LaTeX there. I use /ELL, do a loopy L.
Oh,
I never use a
it's
LaTeX
actually
L.
like
It's
it is L.
yeah.
I'm using two L's to show it.
Yeah, but like LaTeX /ELL does a script L. Which I think I like for variables, but I'm also specific. I use the different Greek letters too.
I love it. Well, you should.
LaTeX is great.
It should be like roughly the same scale.
That's fine.
Okay, that's fine. Yeah, you can look at
them. Can reduce the scale.
That's true. That's true.
It's easier to see if they're the same scale, but you've already drawn some, so just keep going.
Yeah.
All right. Nobody in chat is saying the noise is lethal, so I think we're good. Ooh.
I think that
It's close.
okay. Does any one of those color markers do anything?
Nothing good. It's slightly
This is this is light. This is okay. So we're almost done. We're almost done. Believe it or not, the last exercise is so quick. Like we'll be out of here before you know. Exercise 8. We have two graphs, and it asks us to find a bunch of things about the graphs. Now, this is one of those exercises where if you do your due diligence and read every part, you are rewarded by getting a little short circuit trick.
Yeah. I will say that's going to be a helpful thing in general as a test taking tip, is to read everything before you start answering, but at the very least, read through all the subparts of each problem before you start that problem. I tend to like to actually go through and read every single problem before I start answering any of them. There's also some psychology in that where like your brain can kind of start working on some of the problems if you've already read through all of them. So there's a little bit of psychology there, but at the very least, you can help sort of find some of those tricks if you read through every part of the problem before you start it.
Yeah. Okay, so let's start. The first question asks us to identify all the simple circuits of size 4 in both graphs. So this graph on the left, again, is very nice because there's no crossing edges. So in that case, identifying all the circuits of size 4 just corresponds to finding a polygon that has 4 vertices or 4 sides in this thing. Now, it's kind of unfortunate that in the picture in the exam, this vertex is kind of very small.
Yeah,
So it makes this look like a square, and don't get confused.
so particularly look for the number of vertices,
Mhm.
not just what shape it looks like.
Yeah, exactly. But then, okay, so it's not so hard to identify it in this case, right? We have here, we have this distorted trapezoid. Wow, this was working a minute ago. Okay. Okay, so I'm gonna call it here. That's it. You can think of it because it's a 4 circuit. And you can think of it like 4 vertices connected by 4 edges. Now, of course, sometimes the picture will not be so pretty, right? Like sometimes you could have something like this, in which case you don't have a nice pretty picture. So do not necessarily rely on your geometric intuition to find these things.
Something that can be helpful, Mario mentioned earlier about sort of redrawing a little bit. It's easier for us on the board, but you can do this a little bit on your paper too. These 2 vertices have an edge connecting them. I could think about redrawing that edge around the outside. And now I've got sort of a polygon of sorts. It's got a curvy edge, but I can sort of see the sort of internal shape here by uncrossing those edges and just moving them outside. You can do something similar on this graph too. If you want to see a non-crossing version that doesn't change so drastically.
Now, part C tells us that these 2 things are isomorphic. And because they're isomorphic, if this has 1 4 circuit, then this must also have 1 4 circuit. So we can use that notion to do early stopping when we're looking for 4 circuits in this thing, because when I find 1, I'm done. I don't need to do any more work. So in this one, because the edges are crossing, it's kind of all over the place. It's a little bit harder. But if you notice here, there's a 4 circuit. Luckily, the edges in the 4 circuit don't really cross. So, okay. It's harder. Then you got mixed with the flagging. Perfect. Well, you can kind of see it here. I don't know if chat can see it pretty well.
Jack can see the red on that one. I'm not sure though. You can see the marks.
Yeah, again, this one, I have a nice page that has like very pretty pictures that were different, using LaTeX. So this will correspond to this. Okay, so then part B asks us identify all vertices for which precisely one of its neighbors is on a simple circuit of size 3. So how can we identify simple circuits of size 3? Well, that's going to be pretty easy. It's going to be a similar idea where we can, if we have a nice little laid out shape like this, we can find just like the triangles. We have 3 vertices and we have the edge. And in fact, with triangles, it's pretty nice because you're not going to have this crossy business that you get with 4 or more sides. So
you could, but you'd have to use curved edges. So
well, yeah, I guess so. If you have like a
it would have to be wonky.
Yeah.
Normally
Very wonky.
triangles are going to be nice to you.
Yeah. So it's just a matter of finding the triangles. Finding triangles to identify the 3 circuits. And this is again not I'm just gonna do it like this. It's gonna be this guy. It's gonna be this guy. And it's gonna be this guy. Okay, so I need to find stuff that connects with exactly one of these triangles. Now, everything on a triangle will connect to the triangle in 2 ways, in 2 vertices, right? This will connect to 2 guys. This will connect to 2 guys. This will connect to 2 guys. So we can immediately rule out all of the vertices of each of these triangles. So those are not going to be our candidates. Our candidate vertices for, like, again, a vertex or more that only join with one of the triangles, one of the 3 circuits. So what are the candidates? We have this guy, we have this guy, and we have this guy. Those are the only ones that do not fall on the triangles. So we can see now, okay, is this guy the one we want? No, because it's touching 2, and we want the one that's joined to precisely 1 free circuit. So This one, no. What about this guy? Again, no, because it's touching this one, it's touching this. So not this guy. What about this guy? This is not on one of the free circuits. This is not on one of the free circuits, but this is. So this is our winner chicken dinner.
So one of my students came up with a really clever way to think about this that I thought I'd share. Because I thought it was clever and worked very well. So what they recommended was, because we already know the three circuits aren't going to be in, and also because we know that's what we're looking for, draw an X through each of those vertices on all of the three circuits. Now we're looking for vertices connected to just one X. K has two X's, so it's not bad. D has two X's, so it's not bad. J has just one X, so we're good. I thought that was a pretty clever visual trick to do this pretty quickly, and so that you don't have to keep track of as much in your head.
Yeah. Yeah, that's kind of like usually the theme of the night is try to find ways to simplify all this mathematical complexity. Okay, I wish I had an undo button.
Yeah, I know. I'm sorry, I mutilated your graph.
It's okay. Okay, so this is the guy. So since we have one guy that meets that property, we can expect one guy that meets that property on the other graph. Again, because the adjacency structure is maintained via isomorphism, and we know from reading ahead that these two things must be isomorphic. So where can I find such guy? Well, it would be helpful to first identify all the triangles. Here's one of the triangles or free circuits, right? Here's another one, and here's another one. So we're gonna do the trick, and we're gonna rule out all of these guys.
And once again, we can use isomorphism here. I found three triangles here, so I know not to look for a fourth triangle over there.
That's exactly right. And it might be confusing, right? Because like this kind of looks like a triangle because it's a crossed edge. You gotta be careful. You gotta look at the vertices more than the edges. Okay, so now we need to find the one guy that is only touching one X. This guy is touching.
That's the right one.
Yeah, that's the right one. I wanted to start by. Let's look at the other ones. This one is touching these guys, and this one is touching these guys. So the only one that's left that is the correct one is this guy. So also circle that guy. And again, this is getting a little bit cluttered because I don't have undo. But
Or
you can
multiple
look at the page.
copies. Multiple copies is nice too.
Yeah. Okay, so now we go up to problem C, which asks us to actually find a mapping that relates vertices to vertices. Everything we said about isomorphisms before still applies, but in this one we can proceed in many different ways. The way I show in the page is essentially trying to simplify the problem instead of matching vertices to vertices, matching triangles to triangles. So if you look at this triangle,
Another
Yeah.
trick you can use before we launch into your going through. We know because of isomorphism that the two particular properties we noted in parts A and B have to match up, right? Because those are going to be properties that isomorphism preserves. So J and 3 have the exact same property, and they're the only ones that have that property.
Yeah.
So I know J and 3 have to match up.
yeah,
I know that from the get-go. I also know that the 4 circuit and the 4 circuit have to match up. And J is on the 4 circuit. So the adjacencies of J have to match up with the adjacencies of 3. So from the get-go, if you pay attention to parts A and B, you have 4 of your matching vertices for free, basically, if you pay attention to what you've already done. So that can be, if you get a similar problem, that can be something to pay attention to. Is what I found going to be guaranteed under isomorphism? Because if it is going to be preserved, then you can do those matchings without having to do any more work. Well, ever so slightly more work to get all 4 of them, but it's barely anything. It's essentially free to get those 4 pairs.
Yeah. So I'm gonna do a table notation just to minimize clutter, and I'm gonna do J. We know it's gonna map to 3. Okay. So now, if I want to proceed mapping triangles to triangles, then I can see that, hey, this shape, this 4 circuit shares an edge with this 3 circuit, and it doesn't share an edge with anything else. That structure will be maintained by the isomorphism. So I can look at my 4 circuit here, and I can see that the only triangle with which it shares an edge is this free circuit, which tells us that this thing must correspond to this thing. The question then becomes, what is what? Which vertex is which vertex? Because these are triangles, you can triangulate by finding two of them and then finding the last one, right? So if I want to see which one H corresponds to in here, all I need to do is, again, understand that isomorphisms preserve that adjacency structure, just like Danny noted in the mathematical notation. So if I map J via isomorphism, this needs to still be a neighbor of J, and this is one of the guys that is on both the triangle and the fourth circuit. It's on both, and it's a neighbor of J. So can we find an equivalent one? Well, this one is a neighbor of J, in this case 3, and it is on the triangle and it is on the fourth circuit. So then we can conclude that H must be 1. Likewise, we can see that there's one of them, C, that is also connected to the circuit and the free circuit and the fourth circuit, but is not connected to J. It's only connected to H. So we can look here and we find the other one that is part of the fourth circuit and the free circuit, but is not connected to free. And this is 10. So then that tells us that C is 10. And lastly, there's only one guy left in the triangle, B, and this one must map to the one we haven't touched, which is 6. Okay, so that's one triangle out of the way. Now we just need 2 more triangles and a bunch of leftover vertices that will become obvious
At
later.
this point, it's also worth noting, we have the fourth part of our four circuit force, if we wanted to look at that.
Yeah, we can do that, right? So we have this fourth circuit, we know this, this, and this, so we might as well figure out what this is. So if this is D, which is the one that we haven't touched yet? We know what this is, we know what this is, we know what this is, but we don't know what this is. So then D must be 11. So that's out of the way too. Okay, so now we can notice the fact that this free circuit is joined only to this free circuit. So then we can see that this free circuit is also only joined to one free circuit. It's a little bit hard to see because this free circuit happens to be in here, but this edge joins both free circuits. So that tells us that this inner free circuit must correspond to this guy, and actually also tells us that if B is joined with A in the new free circuit, then 6 must be, and 6 is joined to 8, then A must be mapped to 8. So A, 8. Okay, cool. So what now? Well, we look at these 2 vertices and we have a bunch of ways to proceed. We can definitely disambiguate which one this is, or we can disambiguate which one this is. This one is actually easier to disambiguate because notice that it's the only one that is joined, that's left, that's joined to the last free circuit. So if G is the only one that's left that's joined to this last free circuit, which is the corresponding one in here? Well, 7 is joining to the last free circuit too. So that tells us that G must be mapped to 7. And since we have this and this, that tells us that M must be mapped to the one that's left, which is 5. I'm kind of running out of room here, so I'm just gonna continue it here. Okay, so are we missing anything? We have that, 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 we have that. We have everything except K, right?
We haven't done
the
last free circuit. And
Oh,
also,
right. We've missed an entire free circuit.
And also,
I'm tired, guys. Not an entire piece of table. Okay, so I got this one. Okay, so again, this vertex, by the way, this is called the Frutch graph. It is the one of the 5 smallest qubit graphs with no trivial automorphisms. Or isom, yeah. It's anti-symmetric, or whatever. It has a special name. So you can look at that one if you want to know more about this specific graph.
There's a whole ton of sort of arbitrarily specific or incredibly specific properties that you can put on graphs. There's a lot of research about it. So you can read about graphs for a very long time if you would like to.
Yeah. Okay, so E is on this last free circuit that we're looking at, and it's connected also to the fourth circuit that we're working with on A. So then that must be 12 because it's connected to 11. That's the only one that fits. So then 12 must be connected to 11. No, sorry. D must be collected. D must be 12. Ugh. D must be 12. Gosh, I'm really tired.
Yeah, we've been doing this for 3 hours now.
Yeah. So D is 12. And then lastly, we have K is connected to J in this triangle that we're working with right now. So the only one that meets that criteria is 2. It's the one that's bridging those gaps. So then K must be 2. And are we done? 1, 2, 3.
Not quite. We have to finish the triangle.
What?
We have to finish the triangle.
Oh my gosh.
You need F and L, and then you're done.
F and L. Okay. Okay. Well, now it's super simple, right? Because wait.
Yeah.
F and L. Okay, F is the one that's joined with G. So G is this guy. So F must be 9. And then L is joined with the one we said is K, so that's 2.
4.
So it must be 4. Now I think we're done. And again, once you're done, you should check that you have all the numbers, you have all the vertices, and that there's no repeats.
I think it's tricky because I believe I got skipped on the lettering here.
Yeah.
So you can't just go through the alphabet. You have to actually just make sure that all of the labels are there. I see hand.
I think the D right there should be an E for 12. Yeah.
E and E. Oh yeah. I don't know why I wrote this. Because I already wrote this one. I wrote it. See, that's why you check.
Yeah.
So D should, because D was 11.
D was 11,
Yeah.
so E is
Good catch.
nice. Yes.
Yeah. And that's it for this one. Let's go for this last one, which I promise you
The
is quick.
last question is quick, and then
Done.
we'll be done with this. If you have sort of outstanding questions, at least I'll stay for a couple minutes and see if people have questions.
Yeah, I'll stick on.
But I think we're all running low on steam at this point.
Let me get more sugar.
This goes. They are. Yeah. Oh boy. You ready for this?
Let's go there.
Oh. Okay. Okay. Good. 1.
All right, so we've got some pretty quick yes or no questions to start us off on this. So first thing we want to know is the tree balanced? The answer is yes, because it has sort of the right height structure. Right? We don't have like 3 more children coming off of here that leads to sort of a sort of discrepancy in our sides. Right? So we've got the same height, sort of, no matter what sort of route we take through the tree, if we get to a leaf, we're going to have sort of the same height everywhere. So that's sort of the idea. The answer key just says all the vertices have the same height, which is slightly misleading because it doesn't talk about the level. It talks about the height, which is unique to the tree, not the vertices. So I like to think about like sort of keeping the paths to all of the leaves the same sort of, yeah, the path to all the leaves is the same length, as opposed to thinking about the height of each bird.
One thing to note is that the book defines that a tree is balanced if the highest level is h or h minus 1.
Yes, so
Yes.
I could get rid of of our connection to shoulder, and also theoretically our connection to interstate. And this would still be balanced because there's only sort of one level of difference between these leaves and this leaf.
It doesn't look balanced visually to us humans with our
Yeah,
eyes.
but
But-
there's actually no way to get better than this on
Yeah.
this tree.
And also, like, imagine you had a really large tree, like 1,000 levels. Then, like, the difference between the last level and the previous
Yeah.
level will be relatively very
So
small.
here, the difference between 2 and 1 is relatively very big, while the difference between 1,000 and 999 is relatively very small. And as you get even bigger and bigger, then it gets even more and more relatively negligible. Even though it's still always going to be a difference of 1. So we tend to think more in terms of relative size as opposed to sort of the actual difference there. All right. Other easy yes, no question. Is the tree fully binary? Which means either it's a leaf or it has 2 children because it's binary. So again, we could still have a binary tree that looks like this. If I had something that didn't have interstate and I added interstate into it, I still have a binary tree. I just don't have a fully binary tree because there's this one node that only has one thing. That said, it looks like this. The binary trees and full binary trees have that slight distinction. Yes. What was that?
Could you redefine what balance is?
Yeah, so balanced tree has to have essentially has to have all of its leaves either at the height or at the height minus 1. And so the idea is, like if I didn't have these 2 connections here, then this is a leaf node at the height minus 1, but there's actually not a way to do this such that you have either 2 or 0 children and also have everything at the same height. You could you could move things around such that there was like a single child here and a single child here. And you'd have all of the leaves at the same height, but it wouldn't be a binary tree because you'd have an even number of vertices, but 2 things that had 1 children as opposed to only 1 thing that has 1 children. So a balanced binary tree has to have this property that the leaves essentially have to be within 1 of the height, within a value of 1 of the height. So here, all of the leaves have the value of the height. And so that makes it balanced. But you can also be balanced if you can't complete the last level, you can have things that end only 1 level above it. So it makes it balanced. Does that help? All right. Any questions about this before we answer the last part? So the last part treats this not just as a binary tree, but as a binary search tree, which is technically a slightly different thing. And the idea is now I'm going to search for the word median. So search for median. That is not how you spell that. Median. Yeah, so we're searching for the median, or I guess I should say the word median. And so what we do is at every step along the way, we compare it and go forward based on alphabetical comparisons. So that's the idea of a binary search tree. Usually we think about it in terms of numbers, but we could sort of boil this down to numbers that correlate to alphabetical comparisons, but we can also just do the alphabetic comparisons because we can do that for humans. So highway and median, what is the relative between M and H? Which comes first? H comes first. So we're looking at the right subtree because median is going to come after highway. So first, so I guess it wants all the steps. So compared to highway. And then let's look at right subtree. And essentially all of our steps are sort of going to continue with this sort of pattern. I'm going to compare to something and then pick a subtree to go into. And then I'm going to make a comparison and pick a subtree. And I'm going to keep kind of going like that until I've either found what I'm looking for or concluded that it's not in the tree. So my right subtree starts at road. So now I'm going to compare to road. And what happens with road? Do I go to the left subtree or the right subtree? Left. And now I go to the left subtree. All right, now I compare to interstate. And where do I try to go from there? Yeah, so she doesn't actually have any children, so it doesn't matter which direction I look. It could be in either subtree, but comparing I to M, I believe M will come later than I. So we would be looking at the right subtree, which would be relevant if interstate had a left subtree. Because if it had a left subtree, I wouldn't care about that. I only want the right subtree. If it doesn't have a right subtree, then that tells me, A, I'm really close to the end of my tree. And also B, it tells me that since the right subtree is empty, I don't have what I'm looking for, even though there's a left subtree. So try to look at right subtree. But interstate is a leap. So median is not in the tree. And then if it's asking about a particular program, it doesn't have that in the answer key, but since it's asking what a program would do, I personally would have written something along the lines of then it returns false or null or something to indicate that it didn't find what it was looking for in the tree. But since I suppose it's not necessarily expected that you all have all that much programming experience, because I don't think it's a prereq for this class, then that would be one of the good reasons not to put it in the answer key. But as that's what I would have written, I'll add it here. Return false or null, or etc. Whatever it is that is your program's version of saying, hey, I didn't find it. So false could be a string or a value. Null is usually its own sort of null value thing. Python, I think, called it none. Whatever it is.
Do you know if we have that's like put, we just read it, but like insert
into binary trees?
Yeah.
Yes, there's insert, delete. Usually balance is actually a function. Because you don't want to balance every time.
Leave that for their lead code practice.
Yeah.
So if you want to put something in this binary tree, you would follow this overall procedure. It's just that you also place it.
Yes. So at this point, if I wanted to put median in my binary tree, I would search for it. And then at the point where I conclude it's not there, that tells me here is the place it should go. So I would put median here as the right subchild of interstate. And the left subchild is empty, which I've had professors denote like that. There's different ways. I've seen it other ways too, but I'm going to say the left subchild is empty, but the right subchild exists. Technically, all leaves have empty children, but it's worth noting when I have one child but not the other. However, if I found median, then I wouldn't put it anywhere. So that's why we go through the search before we put it in, because if median's actually already in the tree, I don't want to duplicate it.
And with delete, you would imagine that instead of putting it, it's like you search it, and if it's there, you remove it.
Yeah.
Although you have to be careful because
you have to be careful because if I try to remove road, I have to shuffle around slightly to make sure that the structure of the binary trees are conserved, and B, that I actually connect everything. Because I can't just remove road because now I've lost access to all of these. So you have to be careful with delete. Usually when you delete things, you also rebalance things because you're changing the tree anyway. And rebalancing is an expensive, costly action. So sometimes when you add things, you rebalance, but usually adding things, unless you've added several things, isn't going to unbalance your tree by very much, if at all. So usually it's when we delete and we already have to reorder stuff anyway, that we make sure to rebalance. And then we let the user determine if you've added enough to need rebalancing. Or sometimes the trees actually, sometimes the trees will sort of do some balancing along the way. Sometimes the trees will sort of detect when they need balancing. You can get really specific in how your trees look, but in general, yeah, deletion is the hard part usually. All right, that's it for this problem. So if you have other questions for us specifically, or you want to talk about the bonus problem, we're here for a couple more minutes. Otherwise, we're all done.
Thank you so much. Thank you for participating in the discussions. We wouldn't be doing all this if you guys weren't wonderful students. Thank you for joining in the chat, and we hope you kill it.
Yeah. Best of luck to all of you. You're welcome.
Bye, folks.
Quick question, you